Countdown to the start of this event. I'd like to welcome everyone to the University of Michigan's celebration of the Apollo 50th anniversary. And on this date 50 years ago, the crew of David Scott and Al Worden and Jim Irwin landed on the lunar surface. And so what was remarkable about that crew with respect to Michigan, it's the all Michigan crew. All three of the astronauts attended the University of Michigan. I'm Mark Moldwin, the director of NASA's Michigan Space Grant Consortium, and I'd like to welcome you to this event. And this is also being streamed live on Facebook. If you have any difficulties with Zoom, you can find that link. I'd like to quickly just describe the afternoon. There's a number of events. Our keynote speaker will be looking forward into the future as we celebrate the past accomplishments of space exploration. But I also want to introduce to you Mike Lamone, the director of the new University of Michigan Space Institute that's within the College of Engineering and looking forward to space exploration and new space technology development here at the University of Michigan. Mike?
Hello. Yes, I'm Mike Lamone. I'm a professor in the Climate and Space Sciences and Engineering Department and the director of the new University of Michigan Space Institute. That's an entity which is seeking to be the systems integrator of space research and education across the university. It really is a multidisciplinary endeavor. I'm from climate and space, but my associate director team is from many different places. I'd like to especially call them out as Kathy Sevener from material science, Eleni Georgiou from mechanical engineering, and Mirko Gamba and Jamie Cutler from aerospace engineering. And this institute would not happen without the dedicated and steadfast support of the chairs of both aerospace engineering, Tony Wass, and climate and space, Tuija Pulkkinen, as well as the dean, Alec Gallimore, who we'll hear from in just a minute. We're very pleased to be hosting this event, and we look forward to hearing all of the speakers, especially Pete Ward.
Great. Now I'd like to introduce Dean Alec Gallimore. He truly is a rocket scientist and the dean of the University of Michigan's College of Engineering, and he holds the title of the Robert J. Vlasic Dean of Engineering, as well as Arthur F. Thurnow Professor. He's also a member of the National Academy of Engineering, and his work has advanced our understanding and use of new electric propulsion systems. So, Dr. Gallimore.
Thanks, Mark, and thanks, Mike. Welcome. Whether you're here in Ann Arbor, elsewhere on Earth, or maybe out of space, I don't know, but welcome to our special program. Today, we celebrate the 50th anniversary of the Apollo 15 Michigan and its all University of Michigan crew. David Scott, commander, the late James Irwin, and the late Alfred Worden. Thank you to the various collaborators who have made possible this celebration. Michigan Space Grant Consortium, the University of Michigan Space Institute, and the Space Physics Research Laboratory, in collaboration with the Departments of Aerospace Engineering and Climate and Space Sciences and Engineering. 10 years ago, during our 40th anniversary celebration, I said, quote, human exploration of space is really the most difficult endeavor we as a species have ever done or are likely to do, end of quote. Some people might argue instead for the rapid development of COVID-19 vaccines, yet I stand by my statement. I don't have to tell you, or any of you for that matter, what a challenge space exploration is and why it's worth it. And today's program will provide a wonderful reminder. Apollo 15 met the challenge. It featured the first spacewalk in deep space. It set crewed space flight records for the heaviest payload in lunar orbit and the longest time in lunar orbit, among other records. It launched the Apollo J missions, which were more complex scientific endeavors, and introduced the lunar roving vehicle, the first car humans ever drove on the moon. If that weren't significant enough, the crew also chartered an official University of Michigan alumni club on the moon. Apollo 15 is a milestone in the University of Michigan's proud space legacy. Michigan's impactful partnership with NASA continues to this very day. Among a few recent examples are SUNRISE, which stands for Sun Radio Interferometer Space Experiment. SUNRISE, which was established last year, is a $63 million University of Michigan-led NASA mission to study the sun's radiation effects on the environment for spacecraft and astronauts. This, which is heralded as the largest radio telescope in space, will offer a never-seen-before glimpse of what goes on in the area above the sun's surface, known as the solar corona. Another effort is JANIS, which stands for Joint Advanced Propulsion Institute. Michigan engineers are leaders of a new $15 million NASA center to improve the testing of advanced spacecraft plasma propulsion systems, which could one day propel humans to Mars and beyond. Its director is a three-time University of Michigan alumnus, Professor Mitch Walker, aerospace engineering professor at Georgia Tech, where the project is headquartered. It's co-directed by Professor Ben Jorns, who you'll hear from shortly, who's an assistant professor in aerospace engineering and a member of the University of Michigan's Plasma Dynamics and Electric Propulsion Laboratory, also known as PEPL. And it's also composed of several other University of Michigan faculty members and alumni. And then there's the University of Michigan Space Institute, or UMSI, we call it for short. UMSI was launched late in 2019 in the presence of our keynote speaker and then NASA Administrator Jim Bridenstine. Jim said our approach would be, quote, transformational in bringing departments together under one umbrella, end of quote. Our research program will include representation from all Michigan engineering departments, plus the physical sciences, behavior sciences, and more. UMSI will advance space education through a robust student-built CubeSat program where learners follow the design, build, test, and fly approach, and through community engagement, such as seminars and symposia. Our aim is to maintain and grow our position as the nation's premier space research and education institution. What you are doing in Ann Arbor, we can honestly say is out of this world. As a member of the space community myself, I am especially proud and excited for the future. Apollo 15 astronaut David Scott quoted Greek philosopher Plutarch at a press conference following the mission. The mind is not a vessel, but to be filled by fire or to be lighted, or perhaps kindled, as Plutarch might have actually said. Today, we salute astronauts Scott, Irwin, and Warden, who along with many others continue to inspire us, to kindle fresh ideas and light new fires of exploration every day. Happy anniversary, Apollo 15. I am now pleased to introduce our keynote speaker, Dr. S. Pete Warden. Dr. Warden is a retired Brigadier General in the United States Air Force, Chairman of the Breakthrough Prize Foundation, and Executive Director of the Foundation's Breakthrough Initiatives. The Breakthrough Prizes have been deemed the Oscars of science. They recognize the world's top scientists working in fundamental sciences, and each prize is worth $3 million. Previously, he was director of NASA's Ames Research Center in California until his retirement in March of 2015. He has been a leader in building public-private partnerships internationally. He is a recognized expert on space and science issues, both civil and military, with honors including the Federal Laboratory Consortium Laboratory Director of the Year, Arthur C. Clarke Innovators Award, and NASA Outstanding Leadership Medal. Our speaker holds a PhD in astronomy from the University of Arizona and a bachelor's degree in physics and astronomy from the University of Michigan. Incidentally, I met Dr. Warden nearly 20 years ago when he was an Air Force general and I was a member of the Air Force Science Advisory Board. I wonder if he remembers that. What I do remember is I was immediately his fan back then, and I remain his fan to this very day. Please welcome Pete Warden.
Thank you. Thank you. I'm really honored to be back at the University of Michigan. I did note that some of the PR people thought I was Al Warden's brother. I'm unfortunately not. but I did get a chance to meet Al Worden about 10 years ago. I was the director of NASA's Ames Research Center. And I had just gotten familiar with this thing called Facebook. And one of the first names that popped up asking me to connect was Al Worden, and somebody I had never met but admired a lot. And so we started communicating, and he asked if I would entertain a visit for him out to NASA Ames. And I, of course, so I ended up spending a good bit of a day with him. And of course, the first thing we discussed was he's from Michigan, and his name is identical to mine. And it turns out there probably is a very distant relationship. My grandfather was adopted by the Worden family, and it appears from the same part of the state that his family was from. So not genetically, but at least maybe in terms of background. But the most interesting thing, Al had worked at NASA Ames. In our discussion, he said to me, he said, you have the job I always wanted. I said, really? He said, no, I always wanted to be the director of NASA Ames. And I said, well, wow, that's pretty cool. But I said, you did what I wanted to do. And he said, okay, we're even. And a really wonderful gentleman and an explorer and hero to all of us. So I'm kind of honored to be here in commemoration of the Apollo 15 mission and the University of Michigan. And in fact, I graduated in 1971, and it was that summer when I was actually just beginning graduate work at the University of Arizona. So a great inspiration to me. But what I would like to do is talk to you a little bit about the future and some things that I've been involved with the last few years, and at least some thoughts of where we might go. But first, let me talk a little bit about my organization. Let's see if we get the chart. Here we are. As I said, what I'm going to talk about is the future where actually we become interstellar species. There we are. Well, as mentioned, I'm the chairman of the Breakthrough Prize Foundation, and the Breakthrough Prize started about a little over a decade ago, and it's sponsored by a number of high net worth Silicon Valley billionaires. The founder was Yuri Milner, and I'll talk more about Mr. Milner. He's a physicist by background, is a Russian-Israeli citizen, but he managed to get a couple other high net worth people, including Sergey Brin, the Google co-founder, Mark Zuckerberg, the Facebook founder, and Anne Wojcicki, the 23andMe founder, as well as some input from others such as Tony Ma in China, to start the Breakthrough Prize. Now, the motivation of the Breakthrough Prize is interesting. Yuri and his colleagues noted, first of all, that several $1 trillion have been made the last decade or two by Silicon Valley and its counterparts around the world, and these were based on physics discoveries of a century ago, such things as quantum mechanics and other things that really make modern electronics possible. The concern, though, is that if one looks at a list of the world's most admired people, you see, movie stars, you see politicians, you see billionaires, sports heroes, but very few scientists. In fact, the only scientist that you usually saw on it was either Einstein or Stephen Hawking. And their concern is, how do we inspire the next generation of people to go into science? Not that we don't need these other areas, although politicians I have a question about. But they felt that as billionaires, what they could do is to begin to make scientists both rich and famous. So they decided to start the Breakthrough Prize, and the Breakthrough Prizes are given. There's 7 of them in fundamental physics, life sciences, and mathematics. And the prize is $3 million, which is almost 3 times the size of some Swedish prize I'm not supposed to mention. And so anyhow, it's kind of a pretty cool prize. In addition, we give early career prizes of $100,000 in physics and mathematics. And I'll talk about another prize, which is actually, I think, one of the coolest that we give young people between the ages of 13 and 18. But how I got involved in this, as I said, this started a little over 10 years ago. And I was the director at NASA Ames then, and my chief of staff one day said, came into my office and said, "You'll never guess who's out here to see you." I said, "Well, I don't know. Tell me who's out here to see me." She said, "Well, it's Vanity Fair." I said, "Oh, well, am I the best dressed center director?" And she says, "No, you're kind of near the bottom." But at any rate, it turns out that Vanity Fair, for those in the know, does the coolest party in Hollywood. It's the post-Oscar party. And I've never been, I don't know how cool it is. I've never been invited. I keep hinting I would like to go. But after Uri Milner and his colleagues started the Breakthrough Prize, they were interested in having a ceremony. And they noted that, of course, nobody tunes in to see the Nobel ceremony to see some, the king in white tie give somebody a medal. So they decided to do some sort of Hollywood bang-up thing. And so they asked Vanity Fair to organize the Breakthrough Prize. And their idea was, let's do this in Silicon Valley. And they looked for a place to do it in Silicon Valley. And it turns out if you're in Silicon Valley and you drive down 101, you'll see, about halfway up Silicon Valley in Mountain View, a big government facility with these giant, it turns out they're airship hangars that were built in the 30s and 40s. And so Vanity Fair thought this was a cool place to do it. It's also the location of NASA's Ames Research Center. So as noted, we started the breakthroughs or the Oscars of Science. And they do this actually in the sort of the framework of Hangar 1, which was built for when the US briefly had a airborne aircraft carrier. We built 3 of these in the 30s, the airships Shenandoah, Macon, and Akron. And this was one of the hangars. And these airships were almost the size of the Hindenburg, but they carried about 6 fighter planes. At any rate, we had the ceremony there. And of course, I was the director of NASA Ames. And they always tell you, if you're going to have a big party, invite the landlord. So I got invited. It is a very cool ceremony, and we'll be hopefully having it in person this year in November. Now, as I said, it is kind of the Oscars of Science. The ceremony is for about 2 hours. We have sort of A-list entertainers. The MC are people like Pierce Brosnan and other known Hollywood figures. But it's also the only black tie affair in Silicon Valley, and I have to say that some of these Silicon Valley billionaires, it's kind of hard to persuade them that, okay, black tie doesn't mean black T-shirt, but we're getting there, and it's a pretty neat ceremony, and it's broadcast live by Nat Geo. Now, I'd like to highlight one of the particular winners. This is Jocelyn Bell Burnell, and she was a graduate student at the University of Cambridge in astronomy in the 1960s. And she was working on the brand new radio telescopes that they had built. And she noted a funny signal that was periodic. I think it was something like a second to repeat. She originally said, okay, this might be aliens, and I'll talk more about aliens here in a bit. So she named it LGM1, Little Green Men 1, and took it to her advisors. And they said, "Oh, that's rubbish. It's only the British can do, and don't bother with it." And but she persisted, and it turned out she was able to show that this was a pulsar, the first pulsar that had been discovered, and which is now one of the most interesting parts of fundamental astrophysics. But eventually, she persuaded her advisors, and they published a paper. The sad thing about it was the advisors all won the Nobel Prize, and she did not. And our committee felt that was a great injustice, so they gave her a special breakthrough prize in fundamental physics. To her incredible credit, she took the $3 million along with other resources she had and founded a graduate and postdoctoral fellowship for women and underserved groups in science. A really great person, and it was a great honor for us to be able to provide her with this award and maybe in some measure redress something that should have been done a long time ago. I'd like to talk about another prize we give, and I think this is really cool because I actually chair the committee, but we give the Breakthrough Junior Challenge. We ask young people between the ages of 13 and 18 to do a couple-minute video about some principle of science. And we last year got something like 10,000 entries. The winner gets a $250,000 US scholarship to go wherever they want in the world for study. The school gets a $150,000 laboratory provided by the Cold Spring Harbor Laboratory. But I think one of the coolest things is whichever teacher the student identified that inspired them for science gets a $50,000 check. And what's kind of unique is to give the person that did the inspiration honor. Now, I have to tell you, the first year we did this, this was a young man from Cleveland, Ohio, and he didn't bother to tell the teacher that he'd nominated him. So when we called up and asked the teacher where he wanted his $50,000 check sent, he said, "Is this a call from Nigeria?" And we finally convinced him, no, this is a real call. We're really going to give you a check. But it's a great thing. The students are brought to the Breakthrough Prize ceremony where they're honored along with the other awardees. I'm really pleased that this has been really a global affair. We've had 2 winners from the U.S., but one from India. This year's winner, I don't have her picture on here, is a young lady from Canada. We had young ladies from the Philippines, from Peru, and from Singapore. So it's a really neat thing. And these people are giving me great confidence that we're succeeding in inspiring scientists that are going to bring us forward in the next decades. Now, I'd like to turn now to the main part of my discussion, which is about the breakthrough initiatives. And the breakthrough initiatives were started in 2015. Soon after I joined the Breakthrough Prize Foundation to lead the initiatives. We made the announcement on July 20th, 2015 at the Royal Society in London. You can see Yuri Milner on the stage there with the announcements, making the announcement. And you'll see Professor Stephen Hawking there. Until he passed away a couple of years ago, Hawking was our senior science advisor, and it was a very great honor for me to work with him. He's a true inspiration and a great loss that we don't have him with us anymore. But he was very helpful in defining some of these initiatives. The 3 initiatives are designed to answer fundamental questions about science. The first one was, is there intelligent life elsewhere? Now, whenever I get asked about this, usually the question sooner or later gets to, do we really believe there's intelligent life on Earth? And my question is, it depends how close you are to national capitals. The closer you are, the less likely is to find human intelligence on Earth. So, but this is a very interesting problem. It's often called SETI, Search for Extraterrestrial Intelligence. But I think it's more accurately now called technosignatures, the search for technological civilization elsewhere. And I'm going to talk a little bit about this initiative. The second one is probably equally interesting. Is there any life elsewhere in the universe? As far as we know, there's no life other than on Earth. And I'll talk about a number of initiatives that we have to try to address this question, if there's any life elsewhere. And finally, and this one I have to say is kind of my favorite, is I grew up on science fiction books. In fact, I used to hide a science fiction book in my textbook in school and get in a lot of trouble. So I hope I'm not giving any young people ideas, although nobody uses textbooks anymore. It's all online, so you probably get away with it anyhow. But I've always been really fascinated with going to other stars. I have to say, the first books my mother gave me were 2 little books one was called Planets, one was called Stars. And I thought the planets one was kind of boring, actually, because there were no neat looking aliens or any other cool stuff. They're just like rocks. And but the Stars one sort of mentioned at the end there might be other solar systems and places like Earth. So that was from that moment on I wanted to be an astronomer. And so I want to talk about you know, sort of a dream I've always had. And you know, can we travel you know, between the stars and visit some of these places? Well, the first initiative was Breakthrough Listen. This was the one we announced at the Royal Society. And this is a $100 million 10-year effort to find technosignatures. This is being run for us by the University of California at Berkeley, another school with good colors, I might add. You know, although their gold looks a little wimpy. This has been ongoing now for 6 years. And I'll talk a little bit about some of the efforts there because it's actually pretty exciting. We have partners in time on most of the world's large radio and optical telescopes to look for technosignatures in various means. We've begun to look even at space-based efforts. We're working with the NASA's TESS instrument you see in the center there to identify potential nearby stars that may even have a you know, some terrestrial sized planet that we might be able to observe. I want to just point out a couple of these. We're about to take our first observations on the world's largest radio telescope now, the FAST, the 500-meter radio telescope in China. We also have begun observations at the MeerKAT, which is the first phase of what will eventually be the world's largest telescope. It's on the upper right of these pictures. But it's eventually have thousands of 20-meter class dishes that will be spread over thousands of kilometers in South Africa. The first 64, which has been finished by the South African government, called MeerKAT. We do have a program to use this distributed array antenna to look at the million nearest stars. We're probably going to be starting a similar program with the U.S. Very Large Array in New Mexico, that hopefully we can look out to maybe 1,000 light years and do a complete sample to see if there's signals. Now, I want to put this telescope up. This is, first of all, it's a very cool picture. But this is the Parkes Radio Telescope in New South Wales in Australia. And it's actually a very iconic telescope. It was built in the 1960s. And it was the dish that received the Apollo 11 moonwalk images. In fact, there's a really delightful, family-friendly, I might add, movie called The Dish that was done about 15, 20 years ago in Australia. And it's sort of quintessentially Australian, but it's about the trials and tribulations of using this radio telescope to successfully detect that signal. The reason I put it up, as far as we're concerned, though, isn't just sort of its cool history, but as it turned out, actually last year on Halloween, I was called by the principal investigator of at Berkeley of the what we call Breakthrough Listen program, and he said that we might have a signal, and this has now been identified as Breakthrough Listen Candidate 1. The really interesting thing is that it was the first signal we had in 6 years that really looked like what we expected to see an alien signal. Very narrow band. It was only observed when we pointed at the star. When we pointed off, it wasn't in the beam. It persisted for a few hours, and there was similar signals but lower strength the day before and the day after. So we felt this was interesting as the first potential alien technosignature. Now, the really interesting thing is it came from the star it came from, which was Proxima Centauri. I'll talk a lot more about the Alpha Centauri system, but this is the small star in the Alpha Centauri system. And I'll talk a little bit more about this as well, but that star is now known to have a terrestrial-sized planet in the habitable zone orbiting it. So this got to be doubly exciting. And I'll have to tell you, I'm a skeptic about UFOs being alien things. But when I saw this signal and said, well, if it really are aliens there, this might actually be close enough that they could show up. The interesting thing, we did a lot of extra analysis on this. We're now almost 100% convinced this is not coming from Alpha Centauri or from Proxima Centauri, but it's a complicated form of interference with from some terrestrial or space source that's near to the Earth. We found some other instances that were other places around that time in the sky. It could possibly be some electronic problem. There was a new detector that was used to detect this, but we're not quite 100% certain that it's interference. There are 2 papers that have just been accepted by Nature Astronomy that'll be out here in a couple months. So I urge you, if you have interest, to look at those papers. But we continue to look, but this got us very excited and our hearts pounding for a couple months until we mostly are convinced it was what in the past we think we've seen as interference. Now, let me talk a little bit about the Alpha Centauri system, because this, to my mind, is a very, very exciting system. It's the nearest star system. There are actually 3 stars in the system. 2 of them are sort of the size of the sun. They orbit each other in about 80-year periods. The third one is what's called a red dwarf star. It's about 1/10 the mass of the sun, and maybe 10,000th the luminosity. And it's actually pretty far away from the other 2. It's it's over 10,000 astronomical units, the distance between the Earth and the sun, away from the other 2 stars. And if it wasn't recognized until the last decade or 2 that it was actually attached to the other 2, and technically it's actually a little closer than the other 2. The other 2 stars are 4.3 light years away, and Proxima Centauri is 4.2. Now this is sort of an artist's conception, and somebody told me that, well, you need to tell the artist that not all the stars have the same star spots at the same time. But other than that error, Alpha Centauri A is slightly bigger than the sun. Alpha Centauri B is slightly smaller. I think Alpha Centauri A is a for those of you who are astronomy nerds like I am, it's a G2 luminosity class 5 star like the sun, but a little bit hotter and bigger. Alpha Centauri B, I think, is a B2 luminosity class 5. As noted, they orbit around each other at about 80-year period. If we were sitting where we were orbiting Alpha Centauri A, Alpha Centauri B would be very bright, but it would be about with the orbit of between the orbit of Uranus and Saturn. So far enough out. It turns out that calculations show that both of them could have a planet like the Earth stable for billions of years. So they're very interesting targets. Now, we started a program called Breakthrough Watch that is specifically focused, and we started this again in 2016, focused on the Alpha Centauri system. About the same time, we started our interstellar probe program, which I'll talk about in a bit. But when we did this, we didn't know of proof of any planets in the Alpha Centauri system. But sometimes, just to show that it's better to be lucky than good, in August of 2016, I was called by some colleagues at the European Southern Observatory. They had detected indirectly a planet orbiting Proxima Centauri in the habitable zone, and it's Earth size. And they were nice enough to invite me to the press conference. As you can see, the press conference here, I'll say is an afterthought. We were nice enough to give them millions of dollars to go do an instrument to see if we could, which I'm sure it was in their mind. But this is a very interesting planet, and this is an artist's conception of what the planet looks like. So I guess since the artists do a better job than reality, we don't need to go there. But the planet orbits Proxima Centauri in about 11 days, so it's pretty close to the star. It's only a few million kilometers away from the star, but because the star is 10,000 times fainter than the sun, the amount of energy received on the planetary surface is about the same. Again, we don't know whether it has an atmosphere or oceans or anything else. We just know that its mass is approximately the size of the Earth, and the energy it receives from the star is about similar to the Earth. Now, there's a lot of papers arguing that, well, this couldn't possibly have life. One of the analyses shows that being that close to a star, it would probably be phase locked, which means it's like the moon and the Earth. One phase points to the star all the time, just as the moon points to the Earth. So one side would be heated all the time, and the other side would be cold. So you would have a frozen side and a hot side. Although there is what's called the terminator, where the starlight is on the horizon, that could potentially have, as shown in this artist's conception, could have conditions that are right for life. This is also a flare star, meaning that there are giant explosions on the surface, maybe every few days. Those of the star, those may be sufficient to drive away the atmosphere that this planet could have had at one time. We believe the Alpha Centauri system is about 5 billion years old, so a little bit older than the sun. So this planet could have been blasted by stellar flares for billions of years. Conversely, there are ways that it could be both not phase locked with the star. A good point is in our own solar system, Mercury and Venus can be predicted, they should have been phase locked, but they're not. It turns out they rotate slightly relative to the sun. The reason for that is that they are in a phase resonance with the Earth, and the combination of planets causes these things to rotate slightly. And we already know there's at least one other planet in the Proxima system, so it could be this is actually would rotate slightly. If it rotates and it has a magnetic field, it could have been protected from those stellar flares, just like our magnetic field protects us from solar flares, from stripping away the atmosphere. So it's a very much an open issue of what could be there and what isn't. Now, I alluded to the program that we started. This is the European Southern Observatory's very large array or a very large telescope, pardon me, in Chile. There are 4 8-meter telescopes in this system of telescopes. Now, when I note that this is called the Very Large Telescope, or VLT, it's a little bit embarrassing as an astronomer that we can't figure out better names than Very Large Telescope. I have to say that the European Southern Observatory is building a bigger one now. It's a 39-meter telescope, and that the very imaginative name they came up with was Extremely Large Telescope, or ELT. It's sort of, it gets even worse because it was initially going to be, almost twice the size, and they were going to call it the Overwhelmingly Large Telescope. So now it's just the Extremely Large Telescope. So I guess the next bigger one will be the Awesomely Large Telescope. But if you want to go into astronomy, you should probably help us with our names. But anyhow, we had about 100 hours on telescope number 4, which I think is the one on the right, with a coronagraph, which is an instrument that can block out the starlight, and where we can look right nearby, because the star is a billion times brighter than a planet. But it turns out in the infrared, especially at 10 microns, which is the peak of the energy output of the Earth, the planet's only 1 part in 10 to the 6th times fainter. So we actually had an infrared, what's called a coronagraph, instrument that blocks out the starlight, and we had 100 hours to look at this at both Alpha Centauri A and B, the 2 solar type stars. Now, I put this picture up for kind of an interesting reason. For those of you that are science fiction geeks like I am, this is from the movie Avatar from 2009. And those of you that remember the movie is that humans have launched several starships to this system, that there's a giant planet orbiting Alpha Centauri A, the biggest star in the system, in the habitable zone. And that as giant planets do in our solar system, it had a bunch of moons, one of which is sort of, not only sort of Earth size, but it's Earth-like. It's it's habitable and inhabited. And of course, all the drama is about the human interactions with the aliens on the surface. Now, the reason I put this up is that we have a tentative detection from the 100 hours of a giant planet orbiting Alpha Centauri A in the habitable zone. Now, we don't know if it has any moons, but it sort of raises an interesting possibility. Now, I note that this is a cool science fiction thing, and it was postulated in James Cameron's Avatar series. So we got in touch with James, and he was very excited about this. We have an annual conference, which this year was actually about the Alpha Centauri system, and so we invited him to speak. So this is all done online, but he gave what everybody agreed was the best talk of the whole conference, and talked about how they came up with the mission. And interestingly enough, and I'll talk a little bit about this, that a decade ago he sort of postulated the way we would get to Alpha Centauri as a combination of laser-driven light sails and fusion. So I'll talk a little more about that. And we caught him. He was in New Zealand filming Avatar 2, and he's going to be doing 3, 4, and 5. So hopefully there'll be a lot more avatars. But it was really a great honor to have a great film artist, because I think that will also help inspire young people as it did me, and I think a lot of the folks listening today. Well, let me talk about going to Alpha Centauri. Our third major initiative, which we call Breakthrough Starshot, is designed to actually launch a mission to Alpha Centauri later this century. And the first problem was, how do you do this? And I might add that Yuri Milner has committed 100 million to this. He's also committed 100 million to the Breakthrough Listen program, and we have some programs in the Breakthrough Watch. Ultimately, there may be a lot more. Right now, it's a few tens of millions, but it may end up being hundreds of millions in that as well. So it's kind of nice to find high net worth people that are willing to help us. But I'll talk about the various things shown in this chart, but we've sort of figured out that maybe we can launch in the middle of the century. We'd like the thing to go at about 10 or 20% the speed of light, so we get there in a few decades. The only way we can figure out how to do that today is a very small payload, sort of Graham class, and the target would be the Alpha Centauri system. So we announced Breakthrough Starshot on April 12th, 2016, which was the anniversary of, I think it was the 60th anniversary of, or the 65th anniversary of the Yuri Gagarin's, or 55th anniversary. Since Gagarin's historic flight. I might add that Yuri Milner was actually named after Yuri Gagarin, so he was sort of destined to do cool things for space. But we had the announcement at the New World Trade Center in New York. I was very honored to be there, but I was probably the least noteworthy. There was, in addition to Professor Hawking, which was his last trip to the United States, there was Freeman Dyson, who has talked a lot about interstellar travel. Anne Druyan, who is Carl Sagan's widow and the creator of the Cosmos series. Avi Loeb, who has gotten quite famous lately about discussing potential aliens and suggesting that some of these interstellar asteroids are aliens. I'm skeptical, but interested in listening. And Mae Jemison, who is a former shuttle astronaut and who has also started an interstellar probe. And then that goofy guy that's sitting here talking to you today. But this is a big challenge. The question is, can we go, 1,000 times faster than we can today, which is what you need to go 20% the speed of light. But we point out that in the middle of the 20th century, we increased the velocity we could go by about a factor of 1,000. And the question is, can we do that in the middle of the 21st century? So the first thing we did when we started this initiative was set up a committee. It was actually chaired by Avi Loeb, who's from Harvard. And the first answer we got back was it didn't look good. And but it turns out there had been a fair bit of work done, indeed under NASA sponsorship. The primary paper was by Professor Phil Lubin of UC Santa Barbara that suggested that an older idea that if we could use laser-driven light sails, that we might be able to do this, and the technology was coming along. So based on a number of studies that Stephen Hawking played a major role in, we came up with these objectives, and that we'd like to go later this century at 20% the speed of light. We'd like to fly by the various places in the Alpha Centauri system, hopefully find more planets, and take science data and then mostly images and send those back to Earth. Now, as far as the method, again, I mentioned light sails. This may not be such a young idea. This is a quote from Galileo, or Kepler to Galileo in 1610, that suggested using heavenly winds to sail in space. And of course, people say, well, other than the solar wind, there isn't much any wind, although there is light. And so the idea is to have a very small spacecraft, leave the engine and fuel on Earth, do a light sail, attach a chip to the sail, and we'll talk about all these in a minute, and then use a very powerful laser beam as the wind. We think this is feasible in the next few decades due to a couple developments. First of all, microelectronics are enabling us to pack a lot in a small package, and I'll talk about satellites that are basically, gram class chipsats. Photonics, which has mostly been developed for communications, is advancing very, very rapidly, and we think it's going to get to where we want to go. Now, I will mention that light sails, and this was a commercial one done by the Planetary Society, or privately funded, a decade ago. There's also been the Icarus probe by the Japanese Space Agency that use solar sails, which I'm very excited about. The trouble is the sun doesn't have enough intensity to push light sails to the speeds we want to go. Although I will say that we can get, some fraction of a percent of light speed by doing what's called sun diving. You go in close to the sun with a light sail, and you can get out to maybe hundreds of kilometers a second, which enable us to get to the outer solar system. There are some studies ongoing on this at the Keck Institute and at JPL and Caltech and others that we've been working on. So the concept is feasible. Now, as far as the spacecraft is concerned, if you've got an electronic watch, that chip in that watch does most things a spacecraft does. And they now have, positional accuracy, GPS, cameras, calculators, and so on. And so it turned out that it was pretty clear to us that, can you modify this into a spacecraft? Now, this is Professor Zach Manchester, who was at Stanford, is now at Carnegie Mellon in Cleveland. And he began as a graduate student at Cornell University to start to develop what he called sprites. These are sort of, gram class satellites that he worked with us at NASA Ames, and he recently launched a spacecraft, a CubeSat, a 3U CubeSat, off the International Space Station that had about 120 of these, which deployed them, and they worked very, very well. So I think the era of chipsats is upon us, and I sort of note that a long time ago when I was a student, spacecraft weighed thousands of kilograms, and now they weigh a few kilograms, so it's a factor of 1,000. We think that with this chipsat technology, we can go another factor of 1,000. Very exciting area. Although I noticed that chipsats make people very nervous because you can't track them, and so one person's satellite is another person's debris. But this is an exciting area. And if there are students listening, I'd suggest looking at chipsats. Now, let me talk about the laser. Now, when you go through the calculations, the laser one needs is, again, to kind of take a leaf from the European Southern Observatory, is extremely large, and it's 100 gigawatt class. It has to be several kilometers in scale, And also noting that that Alpha Centauri is in the southern hemisphere. We need to go in the southern hemisphere. We'd like it as high as possible to get above at least part of the atmosphere. So in the Atacama Desert in the Andes looks ideal. Now, I learned something about international politics, which I probably should have known. When we gave our announcement of Starshot, one of the reporters asked us, where are we going to put this array? And so we said, well, Chile, that's the obvious place. One of the things that we forgot to mention was talk to the Chilean government. And so I was summoned to Chile, and I got a chance to have a nice meeting with two of the presidents of Chile. Fortunately, they were both supportive, but you know, the message to self is, you know, in the future, if you mention some country, go talk to them before you make a public announcement. But this looks quite feasible, and this is an artist's conception of the array being fired. Now, we showed this to our sponsor a couple of months ago, and to show you that he's a very good physicist, he said, well, this picture is rubbish. I said, well, what's wrong with it? He said, well, what wavelength are these lasers supposed to be? He said, I thought they were supposed to be 1 micron. I said, well, yes. He said, well, you wouldn't see 1 micron. You know, it would, the eye's not sensitive to that. And so showing that I can sometimes be quick on my feet. And I said, well, that's right, Yuri, you wouldn't see it. But however, there's likely to be dust in the atmosphere, and the laser beam would probably heat up the dust enough so you'd see little twinkles. And he said, okay, that's an artful dodge, but don't do that again. You know, to do, you know, poetic license. By the way, the beam density isn't terribly high. It's you know, since it's spread out over kilometers, it's probably 10 to 20 suns. So you know, people that are worried about breaking down the atmosphere probably wouldn't do that. We would fire that into space. We would have a mothership that would have thousands of these light sails sort of folded up. It would be in a highly elliptical orbit with the apogee at something like 60,000 kilometers. Each orbit, you would launch one of these. It would be hit by the laser for, you know, a few tens of minutes, which accelerates at some modest G load of about 10,000 Gs to 20% the speed of light. Then again, at less than an hour, and then it coast for decades in interstellar space, and eventually would fly by the target. Now we're going to launch thousands of these because, I mean, this is an inaccurate picture because they're not all going to be in formation, but it's accurate in the sense that the light sails have holes in them. Interstellar space isn't empty. There's dust. The gas is actually not going to cause a problem. In fact, it may be an asset that the gas passing through the sail would heat one side relative to the other for several hundred degrees Kelvin, that we could actually pull power out of that for the system. But there would be holes and things where dust hit. In fact, we'd probably lose a number of these things. That's why we would launch thousands. So now this makes it possible to get interstellar distances later this century, I think. But it's a flyby. So one of the questions I just want to briefly mention is, can we go to Alpha Centauri? And you know, this is every science fiction fan who wants to do this, and I'll say that you know, the answer a few years ago was probably not. However, there's some developments. One of those is direct fusion propulsion, and of course we were always sort of told, okay, fusion is the energy source of the future, always has been, always will be. And but there now looks a very promising thing. I mentioned one of them up here because I'm Helicity Space, because I'm actually serving as an informal advisor to them. But this is a bunch of Caltech faculty members that have figured out a way that may make fusion propulsion. You know, I won't get into a lot of the details, but you know, if you figure out if you want to use a reaction drive, chemical systems have a specific impulse of a few hundred. And you calculate how much fuel you need to do to go 20% the speed of light. It's about the mass of the galaxy, so that's not going to work. Electric propulsion, as a lot of you know, is, you know, a few thousand to a few tens of thousands. Fission, direct fission reactions are probably 100,000, but fusion is gets you maybe 500,000. And in fact, it was here a few years ago that one of the students told me that in one of his courses that what you really wanted is 1 million. In fact, that's called the magic million. But fusion with 500,000 could make a multi-stage rocket possible. And so I mentioned there's a couple companies, Helicity Space being one of them. Now, there's always the question of, are there workarounds? Is there faster than light or wormholes or something? Now, my foundation is a little bit skeptical of what we would call speculative physics. However, others are not. Another high net worth person, Cam Kafarian, that we are advising, has set up about a year ago the Limitless Space Institute that is funding studies. They have a few $1 million to look at things that could be really exotic, go faster than light. But they're also looking at things like fusion and light sails. So this looks to be, I think we're seeing an ignition of really cool ideas that I think the stars are going to be accessible in the next century. Now, one final thing is that we are doing some looking at where's life in our solar system, but particularly private missions that could go there, privately funded. There are 5 places that we sort of narrowed in on. Several of them are what are called ocean worlds in the outer solar system. These are worlds, they're moons that have a rocky core surrounded by deep oceans and then an ice crust. Sort of the ones that have been most discussed for potential places of life are Enceladus, one of the inner moons of Saturn, that interestingly enough has plumes of water that are being ejected into space. The Cassini mission actually found simple organic molecules in these. So another one is Europa, one of the Galilean satellites of Jupiter that also appears to have plumes. Titan is actually got an atmosphere in another place. In the inner solar system, a lot of the focus is on Mars, particularly under the surface. There have been detected on Mars potentially what are called biogenic gases that in order to be there, like methane, they need to be restored, and one of the mechanisms is life. But my favorite is this place. This is Earth's evil twin, Venus. And there's a lot of attention now to Venus. The surface is literally hellish. It's, something like, 500 degrees centigrade. But there's a level in the atmosphere about 50 kilometers above the surface where the temperature and pressure are sort of room temperature. It's right in the middle of the sulfuric acid clouds, so that's a challenge for Earth-type life. But last fall, there was a putative detection of phosphine, which is a biogenic gas on Earth. But there's been a lot of controversy over this. There's a question of whether it was really phosphine or it could have been something else. I think the bulk of the data I've seen suggests it is phosphine. The second thing is that it wasn't produced by life. That other life in the clouds of Venus. There's been a number of papers that said, well, life couldn't operate there. There's not enough water. But of course, we used to think life couldn't operate in strange places on Earth, like sulfuric acid hot springs, but we find it there. So who knows? Venus had an ocean probably for 2 billion years of its history. So life could have arisen there and slowly evolved. At any rate, there are plans to send. There's also, government missions. NASA has 2, and the European Space Agency 1 in about a decade. But there's a privately funded mission that we are working with that we'll probably end up putting an instrument on, is by Rocket Lab, one of the startup companies that's done very well in New Zealand and the United States. In 2023 to launch a small probe on a small rocket, and we're working with them at what instruments to put in this. So this is exciting. We're private missions. We've also done studies on a privately funded mission to Europa to fly through the plumes. So I think the era of private planetary exploration for science is beginning. Well, let me stop there and say, so maybe 50 years from now, we'll have our first image of a planet orbiting a nearby star. If we're really lucky, maybe there's really neat stuff on the surface like ruins. If we're really lucky or maybe unlucky, there might be existing civilizations there. Who knows? It's a very exciting future. I think humanity is moving from becoming a interplanetary species to interstellar species. Thanks.
Great talk, Pete. Thank you.
Thank you very much. There's a Q&A button for those who are joining us through Zoom. Feel free to post your questions there, and the moderators, who are hopefully be able to address those over the next 20 minutes or so. But to start, you ended with sort of the age of private interplanetary science investigations. What do you see as the evolution of nonprofit, high net worth foundations, private commercial space companies, and the ESAs, NASAs, JAXAs, Chinese of the world?
Well, I think the future is quite good. One of the interesting things is that most of these recent high net worth people are technical. They grew up with Star Trek and Star Wars. They're all a little bit perturbed, as I was, that governments haven't been doing all this. I mean, I really thought that like my co-named astronaut friend Al Worden, that I was going to get to go to the moon someday, and I might still, but it's less and less likely. So I think there's a lot of excitement about this. The other thing is interesting, and one of the young people I brought to NASA Ames was a young Canadian, Alex McDonald, who's now a US citizen, by the way. He's the chief economist for NASA. And he was a PhD student in economic history at Oxford University. And he wrote a PhD dissertation that I was very intrigued with, it went back and looked, okay, why do high net worth people put money into science? And he went through the 19th century and early 20th century and looked at astronomy, which is my own field. And then he also looked in the early 20th century at rocket development that was largely private until really World War II, just before. And it's interesting that his conclusion was that high net worth people, okay, they were interested in science and they were interested in legacy, but the key thing was they're interested in messaging. And who are they messaging? They're messaging other billionaires. And I sort of, I live most of the time now in Europe, where there's these lovely cathedrals and all of these cities. And if you read the history of the cathedral, you find it was usually funded mostly by some, local duke or prince or, potentate. And, that if you really go back and read, quite often these people weren't really that interested in the greater glory of God. They were interested in impressing other princes and potentates and so on. And so when they go to these parties, that, okay, you're the coolest kid at the party because, you did this neat thing. And I think that maybe even subconsciously that's, part of the motivation. And in fact, you can see that, the recent sort of enthusiasm for suborbital flights that, at Branson, Bezos, and others, and I think Musk will probably go soon, is that it seems that they really are interested in messaging to other. It's not just high net worth people; it's to sort of scientists and other people that they admire, and I think that's going to continue and accelerate. That I think we're returning to an era where a lot of the science is going to be funded by foundations. And we're seeing that the sort of wave of Silicon Valley entrepreneurs is getting to the age where they're starting to think about this kind of thing. And I really have to give Yuri Milner huge credit, and he's an incredibly brilliant scientist. In addition to, he was a PhD student in fundamental physics at Moscow State University. So I think we're going to get there.
Great. A question from a participant. Will the Proxima Centauri probe systems be operating throughout the entire flight, or only wake up with an alarm clock when it arrives?
Well, those are excellent questions. That's an excellent question. We don't know. And a lot of it depends on how much power we can carry. And we have a major study in our Breakthrough Starshot program right now to look at power. How much power can we pack into like some small radio decay device, sort of an RTG at micro scale, versus can you harvest it from the interstellar medium, as I mentioned, going through the interstellar medium. Ideally, well, you probably couldn't communicate to it, but we could get signals back. we'd really like to know maybe once every year or two, are these things still alive? And how many of them are there? Which helps us figure out when they fly by, how to phase the getting the signal. The signal will be sent back by laser. There's clearly some challenges in interstellar space in addition to power. Do you really want to wake this thing up? Whenever you recharge something, or you risk losing it. We did look briefly at them communicating with each other, but then that's how do you know where to point? I mean, it's a very narrow beam. It's something like arc second or so. So it's you have to have very accurate pointing on the. Now we eventually have to have that anyhow to get the beam back to the Earth. But one of the problems is I remember, people that are my age remember when they were kids in the 50s, when your parents would have holiday lights. That these were lights that were wired in series, not parallel. And I remember every year my mother would bring these lights out, and you'd plug them in, and there'd be like 6 or 8 lights, and only 1 or 2 of them would work. So okay, so then you would, and as a kid, part of my job was to go through and you take each light bulb out and put another one in, and then plug it back in. And maybe you get 1 or 2 more that would work because and you've now figured out which. But if there were 2 of them burned out, then it would start to be a big problem. And so, you've got the 2 to the nth. So you end up replacing all the lights, and then if it still didn't work, you threw it away. And I remember this sort of, you don't want to have this link and one of them is out because they can't send some kid out to fix the light bulb. So we are looking at direct beam, but it is an open question on whether you would send that. You would try to at least have them phone home every so often.
And another question, with 20% the speed of light, it's still a several decade trip, and you still are planning for several decades of technology development. How do you sustain a multi-generational project?
Well, that's a very good question. In fact, we picked 20% because that, a lot of NASA missions operate for decades, and some of them, at least the outer solar system ones, it takes a decade or more to get to the destination. That we felt that's the maximum that you could sustain interest. We're also looking at nearer term targets. The outer solar system itself is very interesting for this technology. To me, is one of the most exciting things. Is a couple of years ago, one of our breakthrough laureates, Ed Whitten from the Institute for Advanced Study, postulated that the mysterious planet X, that's supposed to be at 500 astronomical units away, could be a mini black hole. And it's an interesting idea. And his point was the way to figure that out is to send one of these nanoprobes and communicate with it near it. So as it flies by, you can tell by its trajectory, is this thing a compact gravity field or some extended thing? So that's very exciting. Another very exciting idea that I mentioned, the Keck Institute was looking at sun divers, but you could also do this with an early laser system. If you can get out to 500 astronomical units, if you can line up so the sun is between you and a target star, the sun itself acts as a gravitational lens. So it bends the light, and so it focuses. And it's a funny focus, it's a line focus. But the idea, if you have a properly constructed detector, you can fly along this line, you could potentially create images without even have to go there. Now, there's a lot of what ifs, but so we're looking at kind of a set of intermediate missions. So that there'd be excitement along the way that, okay, I can't wait till the big one gets there. And of course, at the same time, technology would march on. Maybe you could, it turns out our system engineering group looked at this and said, well, what if you just built the array bigger? Maybe we can get twice the speed. And so it's possible that you would catch up. You get one that can get there in 10 years. I don't know if you go 40% speed of light. And, if you can go 50, 60%, you get there in, 6, 8 years. So, it's a question of how much money can be put in this. Our target is to build this array for something like tens of billions or less that probably still couldn't be privately funded, but that would be something within the range of space agencies. So we're eventually looking at a public-private partnership. Well, by the way, if it was constructed right, the array has a lot of other potential of sending things throughout the solar system, much larger payloads. Also, potentially, it's got enough power to divert an asteroid that potentially is hazardous.
So again, feel free to post questions in the Q&A feature. Another question, you mentioned Avatar and James Cameron and this Vanity Fair Hollywood type of aspect. Does the foundation work with artists and writers and movie producers to try to inspire?
The answer is yes. I mean, we certainly work with them for the Breakthrough Prize ceremony. I mean, that's the idea is that there's Hollywood meets sort of Silicon Valley, and so there's Christina Aguilera was one of our performers, and of course the MCs are although I will say the first year I went to it, they had Kevin Spacey, so sometimes maybe our choices we're not so good, but we certainly are interested in the entertainment industry getting involved with this. The people like Cameron are very interested in even using some of this stuff and making it, science fiction should, if it has factual possibilities, even more exciting. We did have a program that I hesitate to mention, but I will anyhow. Initially, we had an effort that we called Breakthrough Message. The idea is that, well, let's send a message to, one of the arguments of why you haven't heard anything back from anybody, you haven't called. I'm not sure I buy that argument, but there are people trying to do METI, which is messaging extraterrestrial intelligence. At the same time, there's a lot of people think it's a bad idea. In fact, there was a Chinese science fiction series called The Three-Body Problem a few years ago that said that, by messaging, the Alpha Centauri system, as it turned out, we attracted their attention, and they decided, well, the Earth is a much better system, and so they mounted a big invasion. And this is called the dark forest. The reason that you don't hear any sounds is because everybody's afraid of making noise and attracting predators. I'm skeptical, although I'll say that Stephen Hawking was not. I mean, he was very negative, and there were others. But initially, the question of artist is, we were going to have a contest really to say, what should this message say, and how would you transmit it? I mean, but what it would say would be images, we thought, and Ann Druyan was leading that effort for us, and she was, along with Carl Sagan and others, made the golden record, and so it was clear to us that there was, and we had a couple artists that we brought in. We originally were looking at working with MoMA in New York, so that we're very much interested in that. We may still do something in this area, but I think if we do it, we're going to make it very clear that what we're doing is not about sending anything, it's about thinking about it. I mean, the best time to think about what to say is before you get a phone call.
Thank you. Another question was, since the probes are going to be lasting decades, do you envision them being sent towards other promising destinations further away, or as they go past Alpha Centauri, continue to operate?
Well, once they fly by Alpha Centauri, they're going to be, we have a little bit of ability to maneuver them slightly. Maybe we could put small photonic lasers on, so we might be able to move them a fraction of an arc second, which is enough to make a course correction to get closer to the planet we want to image. But the answer is very much yes. We think that within about 3 parsecs or so is probably roughly 10, 12 light years is accessible with this technology. As I mentioned earlier, that perhaps we could go a little faster. So we'd like to do these in a few decades. One of our objectives of the Breakthrough Watch program, and we have a small satellite we just started that will look at Alpha Centauri to see if there's small motions of the two stars relative to each other. This is being led for us by the University of Sydney in Australia, that you could detect a planet. We're also going to look at at least one other system that's our binaries that could have planets, the 61 Cygni system. We have some other programs we're at study phases of that we would probably look at things out to 10 or 12 light years. We know there's planets orbiting a couple solar type stars, Tau Ceti and Epsilon Eridani. Tau Ceti has always been very interesting. It figures prominently in science fiction. It's about 11 light years away, and we know it has a number of planets, including one. I think it's got 5 planets that we detect indirectly. That one of them, it seems to be sort of terrestrial sized in the habitable zone. So, and we also are finding out that virtually every red dwarf star has planets. And of course, there's 70% of the stars in the galaxy, and so most of the nearby stars are these red dwarfs. It seems that when you look carefully at them, most of them seem to have an Earth-sized planet orbiting pretty close. So potentially there's a lot of other targets. I think there may be. I suspect we'll eventually find, of the 50 nearest stars, maybe 5 or 10 are interesting targets. Of course, we got a signal from one of them that sort of changes that. Maybe in many ways.
For the radio telescope search, how far away is the star system that you can actually detect a signal?
It depends how powerful the signal is. I mean, the initial, there was a paper that started modern SETI was by the 1959 by Morrison and Ciccone, which calculated that modern radio transmitters, like on a big radio telescope, could be seen halfway across the galaxy at about 1.5 gigahertz. And so that's really kicked things off. We started to look. If we had something, the size of Arecibo with the transmitter it used to have before it fell down, we could probably transmit across most of the galaxy to a civilization like ours and be detected. So the idea is, okay, so we're mostly focusing at the nearest, 1,000 light years or so. Another reason for that is that if somebody was capable of watching the Earth, even from a distance, that what would be the first indication there might have been a civilization here, a technical signal of civilization. And it turns out, arguably, that was about 2,000 years ago, that the Romans burned down most of the forest in what's now Spain to smelt silver. And that changed the atmospheric composition with whatever the industrial pollutants. Those would be in principle detectable. So if you say, well, when would they have seen that? So that goes out to 1,000 light years. So it's 1,000 light years to signal back. So we want to do a pretty complete sample of that. We also want to look at places that has a high density of stars. So we're scanning the galactic plane, and of course since the southern hemisphere points more towards the center of the galaxy, we're using that Parkes radio telescope to scan the galactic plane. We're also looking at about 100 of the nearest galaxies. There would be incredibly powerful transmitter. And then we're also doing selected searches that if we find from missions like the TESS mission that there's a planet a star that has an eclipsing planet, it turns out if it's eclipsing, they may be trying to transmit to things that could see them in the eclipse. And so we've got a few dozen of those. We're looking for other things that might be solar analogs. It turned out that when the sun was formed 4.5 billion years ago, it was undoubtedly formed in what's called an open cluster. It's a cluster of stars. And the stars were pretty close to each other. They were maybe a few tenths of a light year. And that's close enough so they could have, to use the not technically correct, they exchanged spit. So if one of them got life arose or started, it could infect the others. And so, a good place to look is at the sun's siblings. And so we've got a program there. There's one that we're pretty sure is a solar sibling. It's a star like the sun, a little bit bigger. and it's about 100 parsecs away, so 300 light years. So we're trying to look at that and say, okay, it's the same age. If there was life emerged on Earth or there or some other place in that star cluster, it probably all at the same time. So who knows? So that anything we can do that kind of maximizes it. We're trying to look at different radio and optical frequencies.
What is the estimated cost to get to Alpha Centauri and our high net worth investment fund sufficient, or is there a business model?
Well, that's a very good question. And it's one that my sponsor asks all the time. We finished the first phase of our laser work last fall, and he quite frankly raked us over the coals, for good reason. And his biggest concern wasn't the technology; it was the cost. And he said that, well, he did a couple of things. One is he talked to the head of Foxconn, who makes cell phones, and asked him if he thought they could do this. And he said, well, sure. He said, they have a plant with 1.5 million people. You could make a plant like that. And of course, the materials alone as that we currently understand how to make lasers would be tens of billions. So that's probably, hundreds of billions. That's clearly out of the range of even what governments would do. So our question is, can we build these things for tens of billions? Those are still higher than high net worth people would do, but they are within the range of what high net worth people might do to start it and build prototypes. Major telescopes that are built privately are now $1 billion or $2 billion. But most of these things are now public-private partnerships. So we're kind of looking at a public-private partnership where maybe $1 billion or $2 billion would be funded by us and other high net worth people. But then get governments, if we can make the cost in tens of billions, then it becomes comparable to the James Webb Space Telescope or the Large Hadron Collider. And a mission, particularly if we start finding some indication of life orbiting these nearby stars, that's kind of feasible. So it's a real partnership we're looking for.
The most recent Virgin Galactic and Blue Origin sort of split public opinion on if it's really good or just billionaire playthings. And if private spending on space exploration exceeds public spending, is there a public good that could be argued in such a transition?
Well, that's a very complicated question. There's many different aspects. First of all, I doubt that private spending will ever exceed space spending of governments. And one of the big reasons is there's a huge security implication. I mean, frankly, much of our focus on the last few years has been competition with China and others. Some of it's economic competition, but you have not just the United States, but other countries are forming space forces, and the attention is now shifting away from just the Earth to cislunar space. So I think it's never going to get to the point where the majority of funding is going to be private. Conversely, private things can do high risk stuff. And give you an example, when we started the Breakthrough Listen, it was $100 million US. Yuri Milner was there, and we had Hawking and the former head of the Royal Society, Lord Martin Rees, and the Astronomer Royal, and Frank Drake, who was really the grand old man of this area, Ann Druyan, and Poppy Loeb, and a few others. And so Yuri asked, we were all kind of sitting around, he said, about 20 of us, he said, we're about to announce this. What do you think our likelihood of success will be in the next decade? We're going to find an intelligent signal. And the numbers kind of range from 0.1% to a few percent. I forgot what Hawking said, but it was, I think he was one of the more optimistic. And I think my number was 1%. And so at the end of this, I asked Yuri, I said, well, Yuri, what do you think the probability is? Because he was funding it. And he said 10 to the minus fifth. I said, well, that's kind of interesting. It was the lowest number. I said, I worked for the government for an awful long time. I said, if I'd have gone to the government, to Congress, to a committee and said, like, I'm going to do this really cool thing, and the expert enthusiast recommendation is maybe 1% success, and it cost 100 million, I'd have got thrown out of the hearing. And so I said, okay, these are the kind of things that are high risk, high payoff, that are likely to be funded by really philanthropists, and they're not really doing it for, as I said, anything other than their own personal reasons. So I think that's going to happen. So putting a private settlement on Mars is a high risk endeavor. I don't, you look at governments, nobody's really interested in settling these places. I think the moon's a lot cheaper. I think the moon is easily doable within private, a few billion. In fact, we had a little workshop about 6-7 years ago in Silicon Valley where our conclusion was a few billion, and it was attended by the Google founders and a few other billionaires. So I suspect that those are the kind of things you'll see. That's still a lot less than governments, but it will take on the high risk things. I mean, our efforts are, they're all high risk, and they're, in the end, I think if we lower the risks, governments will help. But I think there's a real synergy here.
Thank you very much. I don't see any additional questions in the Q&A. And so to try to keep on our schedule, if it's okay with our next speaker, Dr. Hillberger, we're going to take a 20-minute break and come back at 2:50 for building a sustainable presence on the moon.
Right. Just one final thing I just want to say is go blue.
Go blue. Thank you very much. So we'll be back in 20 minutes. And our next speaker this afternoon, I guess it depends on your time zone, is Dr. Mark Hillberger, a senior research engineering in the Space Technology Exploration Directorate at NASA Langley. He received his two of his graduate degrees in aerospace engineering from the University of Michigan, and his undergraduate degree in mechanical engineering from Rutgers University. And he will be presenting some of the work on new technology in structures. So, Mark.
All right. Can you hear me okay? All right,
Yes.
great. So I'm going to try and share. I've got a PowerPoint, and then I have to break out a PowerPoint a couple times for some videos. But hopefully everything will work all right. So it is afternoon where I'm at, so good afternoon. And I just want to say I'm really excited to join everybody for this 50th anniversary celebration of Apollo 15. I first really want to thank the organizers for inviting me. And I'm a third generation Michigan engineering grad, so blue blood runs true through our veins at my house. So it really is a great honor for me. Just as a side note, my grandfather graduated from civil engineering department in 1927, and my dad graduated from mechanical engineering in 1959. So anyway, if they were here, I'm sure they'd be celebrating with us. So thank you so much for the opportunity. During my presentation, I'm going to talk a little bit about what the future may look like as we venture back to the moon, and how we will achieve a sustainable and permanent presence. I'll focus primarily on the construction of infrastructure and the use of local resources, but I'll probably touch a little bit on other related issues along the way. So, but before we do that, we'd like to step back and celebrate the past. It's been more than 50 years since NASA landed the first humans on the moon during Apollo 11. And of course, today we're celebrating the 50th anniversary of Apollo 15. I was only 6 months old at the time, so I sort of missed all that excitement of the Apollo era. But we have a new era upon us that I'm excited to talk to you a little bit about today. But since then, our lessons learned from Apollo and other space exploration activities have led to decades of advancement in technology and science through innovation and collaboration with industry and academia and other government agencies. Examples such as the International Space Station are now emerging in very successful commercial space entities, along with our recent exciting missions to Mars, including that Mars helicopter, which I cannot get enough of. But you just have to say that the impact of Apollo and the other space exploration efforts that we've had over the years have impacted our lives in so many ways, but they're just so difficult to measure. I'm really excited to be on the edge of what I think is another exciting chapter in space exploration. So NASA, as I'm alluding to, is embarking on a new set of missions with Artemis. The Artemis missions will be to do something similar to what Apollo did, but this time the vision is a little bit different. This time we're going there to stay. The plan is to establish a cadence of commercial and NASA missions in order to provide foundational elements and demonstrate technologies that will enable a sustainable presence on and around the moon. The moon will also provide us with near-Earth location where we can test the systems and technologies that we need to one day send astronauts to Mars and back. So before I get into the meat of my presentation, I want to start with a short video about the Artemis program. I think it'll provide a pretty good background on what NASA's vision is with the Artemis program, and it'll dovetail nicely into my discussion on developing infrastructure and capabilities for a sustained lunar presence. So let me break out of this for a second and see if I can pull up my video. So this video you can find online. Let's see. Make sure I'm sharing the right one. There we go.
50 years ago, we pioneered a path to the moon. The trail we blazed cut through the fictions of science and showed us all what was possible. Today, our calling to explore is even greater. To go farther, we must be able to sustain missions of greater distance and duration. We must use the resources we find at our destinations. We must overcome radiation, isolation, gravity, and extreme environments like never before. These are the challenges we face to push the bounds of humanity. We're going to the moon to stay by 2024, and this is how.
This all starts with the ability to get larger, heavier payloads off planet and beyond Earth's gravity.
For this, we designed an entirely new rocket.
The Space Launch System. SLS will be the most powerful rocket ever developed.
And with components in production
And more in testing?
this system is capable of being the catalyst for deep space missions.
We need a capsule
that can support humans from launch
through deep space and return safely back to Earth. For this, we've built Orion.
This is NASA's next generation human space capsule.
Using data from lunar orbiters that continue to reveal the moon's hazards and resources.
We're currently developing an entirely new approach to landing and operating on the moon.
Using our commercial partners to deliver science instruments and robotics to the surface, we are paving the way for human missions in 2024.
Our charge is to go quickly and stay, to press our collective efforts forward with a fervor that will see us return to the moon in a manner that is wholly different than 50 years ago.
We want lunar landers that are reusable,
that can land anywhere on the lunar surface.
The simplest way to do so is to give them a platform in orbit around the moon from which to transition.
An orbiting platform to host deep space experiments and be a waypoint for human capsules. We call this lunar outpost Gateway.
The beauty of the Gateway is that it can be moved between orbits.
It will balance between the Earth and Moon's gravity.
in a position that is ideal for launching even deeper space missions.
In 2009, we learned that the moon contains millions of tons of water ice.
This ice can be extracted and purified for water and is separating oxygen for breathing or hydrogen for rocket fuel.
The moon is quite uniquely suited
to prepare us and propel us to Mars and beyond.
This is what we're building.
This is what we're training for.
This we can replicate throughout the solar system.
This is the next chapter of human space exploration.
Humans are the most fragile element of this entire endeavor, and yet we go for humanity. We go to the moon and on to Mars to seek knowledge and understanding and to share it with all. We go knowing our efforts will create opportunities that cannot be foreseen. We go because we are destined to explore and see it with our own eyes. We turn towards the moon now, not as a conclusion, but as preparation, as a checkpoint toward all that lies beyond. Our greatest adventures remain ahead of us. We are going.
We're going.
We are going.
We are going.
We're going.
All right. That always gets me kind of fired up. But I hope you enjoyed that quick video. Let me get back to sharing my presentation. And all right. So hopefully you're seeing the presentation okay. So they said pretty emphatically that we're going. And I believe them. We're making great progress towards this mission. But as we look forward, you've got a question, how are we going to live and work when we get there? What are we going to be able to build in terms of infrastructure? Well, NASA started many new activities to complement this Artemis program, such as the Lunar Surface Innovation Initiative, to focus on many of the key technology areas that are going to enable long-duration sustainable settlements on the moon. And you can see in this chart here some of those areas, including surface power, technologies for surviving extreme lunar environments, such as incredible thermal swings, very, very low temperatures at night and higher temperatures during the daytime. Lunar dust has turned out to be, and as observed by Apollo astronauts, can be a significant issue associated with the operations of rovers and the performance of the spacesuits, as well as if the dust is to get inside of any of the vehicles or habitats, can cause health issues. So dust mitigation turns out to be a big challenge and a significant focus area for us. And there are others, as indicated by this chart. I'm just going to be focusing primarily on surface excavation construction and how we might build the necessary infrastructure. And I'll also talk a little bit about in situ resource utilization and its importance in providing the materials necessary for construction. So let's first talk about what sort of infrastructure we might need. We can envision a moon base where we have reusable landers that are coming and going, a nearby settlement that includes living and working spaces for astronauts. So we're going to need launch and landing pads that are going to provide safe landing locations, but also help control the dust and surface plume interactions. So the rocket plume comes down and hits the lunar surface and throws out regolith ejecta, which can turn into essentially projectiles that can damage local surface assets. So it's an important consideration to have properly designed landing pads for these vehicles. It's likely that we're going to need some type of prepared roads to enhance traversability of our lunar rovers, as well as, of course, habitats, shelters, refineries, and greenhouses, and finally power plants. So that's a lot of stuff. And each of these different types of elements are going to have unique construction requirements, whether it's high temperature materials for the landing pads or airtight, damage resistant, radiation resistant shelters for human habitation, or power plants if we're thinking of nuclear type power plants, then proper shielding and even cabling. How do you transmit power from the plants into the facilities where you need it? So a lot of things that have to be developed on our way to realizing this vision. So I'll now focus more on how we can build infrastructure and the various types of or classes of infrastructure. And so we break it out into 3 classes. And this is kind of a busy chart. This is the only chart that I have that's like this, but I wanted to spend a little bit of time talking about these different classes of construction. And on the left, you see a chart that's indicating sort of the technology level versus evolution or time. And so the first class we call pre-integrated, and in the upper right you can see in the table different characteristics of a class 1 pre-integrated structure, but it's essentially similar to what's used to construct the International Space Station. It's fabricated on Earth, it's pre-integrated with all the systems and delivered to its final destination, ready to use. It has the benefit in that all these systems have been integrated and they've been checked out on Earth, and so that of course reduces risk to the astronauts and of course the immediate habitation capability. However, this approach is obviously limited by the size of your launch vehicle, not only the size of the payload shroud, but the mass that the vehicle can deliver to its destination. And as many of you probably recall, the International Space Station modules were constrained to the Space Shuttle orbiter size and mass capabilities, and so it required not only these small volumes, but also many missions over periods of years to construct the entire space station. Next in class, we have class 2, which is prefabricated deployable type structures or structures that can be assembled in space from parts. So this type of construction can be used obviously to build large truss-based structures, observation platforms, or maybe for Dr. Warden, we could build him an enormously huge, gigantic space-based radio telescope. That's something that might be of interest. Examples of deployable structures that we currently use would be solar arrays and thermal radiators on the space station, as well as inflatable structures. And some of the obvious benefits of having an inflatable habitat or a deployable structure is that they can be stowed in a very compact volume and then be expanded into very large volumes. Class 2 construction does share a lot of the same benefits with class 1 in that many of the subsystems can be pre-integrated and tested prior to launch. However, it's typically expected that some assembly is going to be required and some final checkout will have to be completed before the system can be occupied or used by humans. Deployables or in-space assembly of structures also helps reduce the restrictions on payload size and mass restrictions that you might have due to your launch vehicle. So you could potentially launch a very large habitable volume on a much smaller launch vehicle. But maybe one drawback would be you're still launching everything from Earth. So this is where the final class 3, really shines, and that is construction, which is based on the utilization of in situ derived resources, that is living off the land. So resources derived from the local materials. This approach obviously can significantly reduce our reliance on launching materials and structures from Earth. It provides us tremendous flexibility in the size and the shape of the constructed structure, as well as allowing us for easy future expansion or even repairs of existing structures. However, as you'll see in the coming slides, we do have a lot of technology development work to do in order to realize what we think is the ultimate capability. It is by far the least mature of the three classes of construction. So I'll spend the remainder of my time talking about Class 3 construction on the lunar surface, as it's generally thought that this class will provide us with the greatest long-term promise. So, let's see, next chart. Oh. Let's see. Oops, sorry, froze up on me a second. All right, so maybe the first obvious question, which probably has an equally obvious answer, is what are we going to use as our building material? And the obvious answer is the regolith, the dirt that's on the moon. You can either use it in a bulk form, where maybe you mix it with a binder, or you sinter it into a brick, for example, and use that as a construction element. Or the regolith can be processed into specialized materials such as metals or ceramics. So, you know, we can readily manipulate regolith into simple berms, or we can compact it into paths. However, we expect that regolith structures such as 3D printed houses or habitats will require some type of rigidization to take the structural loads. So early concepts may require earth-based binders or polymers, but later transitioning into lunar source binders, such as some of the metals that are present. We do know from Apollo samples and more recent global surveys of the moon that there is a tremendous amount of resources for us to take advantage of, and will be the basis of our sustained existence. And just an interesting aside, I'm not sure how many people have seen a picture of what a little piece of regolith looks like, but it's not like a grain of sand. It's a sharp-edged particle, and the environment on the moon does not promote erosion like we have here on Earth, and where we get nice rounded pieces of sand, for example. And this was one of the troubles that astronauts immediately picked up on, is that these dust particles would become embedded in their suits and cause their suits to abrade over time. It would also get into their cabin. It could become a health hazard, clogging air filters and that sort of thing. It could also potentially compromise instruments and seals and mechanisms in their surface assets. So again, as I mentioned earlier, dust mitigation ends up being a big challenge for sustained lunar missions. All right, so we've sort of settled on regolith as being our building material, but we need systems to identify and map out the lunar regolith resources. And as I alluded to, we do have orbital assets that have been used, including Lunar Reconnaissance Orbiter and other orbiters that have been able to map out nearly the entire surface of the moon, identifying locations of different types of materials and water ice, for example. We have a very good understanding now of what types of materials are available and where. We're also planning our first dedicated mission called Viper, Volatiles Investigating Polar Exploration Rover, slated for 2024, used to do the first detailed ISRU resource mapping and detailed mineral or material assessments. So this is obviously a very important first step in identifying these resources on the lunar surface. Once we've identified the locations of these desired materials, we now need to have ways of excavating and processing these materials and this regolith into building feedstock, such as size-sorted aggregates as well as binders. I've pictured just a few of the many excavator concepts that we currently have going on at NASA, including one called Razor, and it's being developed at Swamp Works Kennedy Space Center. And it has an interesting design. You can see a center section there that is a lightweight mobility system, and then on both ends we have some counter-rotating bucket drums. And in the next video I have, you'll be able to see Razor in action. It has a really unique design, and there's a reason for it. But before I tell you the answer as to why, let's watch this video. So you can see the Razor hopefully coming, and there's the front bucket drum attached to a lightweight mobility platform. It acquires the material, and then it's going to approach a hopper, and it's going to unload this material into the hopper. There you go. It's done unloading that material, and then the hopper is going to take it for processing into whatever they want to process it into. All right, so we like to call these our blue-collar robots. These robots are doing the dirty work. They're getting down and dirty and working in very difficult conditions. Some of the challenges include, obviously working with abrasive materials, which are going to lead to significant component wear over time. Some of our mission requirements are looking at excavation of many metric tons of regolith over periods of years. So we have to be able to understand how these components wear. It would be very beneficial to have structural health monitoring systems as well as repair strategies, and to do this all in an autonomous fashion. Those are some of the unique challenges of having a blue-collar robot. But one of the other challenges, and this gets to the design of the Razor, is that when we see these lightweight lunar excavators, they have a really low reaction force that they have to work with. So if you think about terrestrial machines, they're very heavy. They can dig up large quantities of material without any problem. They hardly move, and the excavator just goes in and scoops out the dirt. Well, on the moon, we have reduced gravity, so we're at 1/6 of Earth's gravity, and then these machines are necessarily really lightweight because we can't be launching enormous caterpillar bulldozers to the moon. And so the result of that is low reaction forces on the wheels by which the excavator can react against while it's doing its work. Well, the Razor's design, as you can see, is utilizing a counter-rotating bucket drum. So these counter-rotating bucket drums essentially cancel out any sort of reaction or push-off forces, essentially equalizing the forces. It appears to work pretty well in this laboratory environment. The plans are to be sending a mission of a vehicle like this to the moon in around 2026. So, okay, so we've got our materials now, and they've been processed. So now we're about ready to get with our construction. First step there is doing autonomous site preparation. So this would include things like rock clearing, grading, leveling, and compacting, all again being done autonomously. Here we have in the upper left figure a chariot, which is a multi-purpose robotic platform. It can be used to mount different construction implements on, including the blade, as is seen here. You can also mount a manipulator crane to do offloading and asset positioning, or a scoop or bucket on the front of it. As I mentioned, autonomy is a big part of this, as well as site verification. Before you go and build your house on your new plot of land, you have to verify that your site has been prepared to the correct compaction, that there's no local areas of discontinuity that might cause foundation cracking, that sort of thing. So we have to have inspection methods and data processing capabilities that will verify that our surface preparation has been done correctly. Autonomy is particularly challenging, and when I talk to the folks that work with autonomy and robotic systems, this becomes a particular challenge to them because you're consistently and constantly changing the terrain, because you're moving it, you're manipulating it, you're working it. That terrain is often used to help with decision making and path planning, how the robot is going to operate. So the autonomous system has to be able to characterize and adjust to the changing terrain on the fly. So obviously a very important and challenging problem. So next step, we've prepared our surface, and finally we're at the phase of constructing something. And here I'm going to highlight class 2 and 3. I said earlier I was just going to talk about class 3, but really I'll talk a little bit about class 2 as well, because I think both are going to play a very key part in building sustainable lunar settlement. For example, we have the Armadas project, which is one of several projects we have working in the area of class 2 construction. They're working on autonomous assembly of truss-based voxel structures for surface and in-space structures. So both surface habitats and towers for communications and that sort of thing, but also in-space structures for building next generation telescopes and that sort of thing. The project's done a tremendous job. Their primary focus really has been on the autonomy and less on the truss structure itself. But very, very promising work going on in that area. And then finally, class 3, which is what I would consider to be sort of the holy grail of construction, and that is 3D printing of structures using lunar resources. And you can see on the bottom right there a picture of a contestant back in 2019, I think was the runner-up in the Printed 3D Habitat Challenge. It was actually Penn State, so another Big Ten. Did a fantastic job building this, designing and building this 3D scaled model of a lunar habitat using 3D printed concrete. Well, one could also envision sort of a hybrid between class 2 and class 3, where maybe you'd use in situ resources to produce the piece parts like the truss structures and that sort of thing, panels, and then assemble them into a final structure. So I think the opportunities and the options are wide open at this point, but we're making a lot of progress along a lot of different fronts. So I'm going to switch back out one more time and show one video, and then I just have a few more slides. And this video is 1 minute long, and it's showing the 3D printing process developed
50 years ago,
by
we pioneered a path to
Icon. Oops, wrong one.
the trail we blazed, captured the fictions of science, and showed us all.
How did that happen? Let's see. I thought I clicked on that one. Ah, here we go. Yes. And I see I have a time warning. I will be done pretty quickly after this. So here, this company Icon is developing low-cost housing in the Southwest. I see them building a house here. All right, that is really cool. When I retire, I'd like to retire to a 3D printed house. They're available already, so why not? All right, so back to the presentation. I just have a few more slides here. So what you couldn't see really was a bird's eye view of what that gantry 3D printing system was building. It was building what you see here in the lower left, a series of 2,000 square foot homes. ICON's vision, though, is to extend this capability to a lunar-based construction capability. And so on the upper right, you can see a concept for the internals, anyway, of a landing pad. There would be a final layer that would go on top, some sort of plate or something. But here you can see the intricate internal construction of this landing pad. And so when that rocket plume comes down, it interacts with this tortuous path, essentially taking out the energy from the landing plume. So very elegant design, and they actually tested it, and it survived a simulated rocket blast. But as you can see in my box here, some of these unique challenges that we have in translating this type of technology to a lunar-based technology is generating materials and processing that will work in the lunar environment. So, the vacuum, radiation, extreme temperatures. They're working very hard in developing a variety of different material concepts and processing techniques, and they're making great progress, but it is definitely a significant challenge. There's also, again, the inspection and certification aspects. A lot of these activities that we're going to be doing on the moon are autonomous. And when you're building something for human habitation, certainly before you go and use it, you have to have a way of verifying that it's safe to use. And then I have a few other challenges there, but I'll move along. I felt like I couldn't finish this story without restating or acknowledging our dependency on the many other technology areas that LSII is currently supporting, including power and survive in extreme environments and dust mitigation technologies, but in particular the in-situ resource utilization. And we have to work very closely with NASA's ISRU team. But ISRU provides more than just construction materials. As was mentioned in the video, there are other consumables that are going to be needed to support sustainable human settlement, such as air, water, and propellant. So there's a tremendous amount of effort going on right now at NASA to develop these needed ISRU technologies to make all this happen. But finally, I do want to say, and this sort of goes along the lines of some of the comments that we finished up the last talk with, NASA is working hard to develop and demonstrate some of these basic technologies and capabilities, but our ultimate plan really is to transition them to commercial partners. In this way, as we're seeing with launch vehicle and lunar lander markets, new commercial-driven opportunities will emerge. We expect costs will come down, and this will be the beginnings of a robust space economy. It will truly enable sustained off-Earth living and provide us a step-off point for our human missions to Mars. And that was it. I hope you enjoyed the presentation.
Thank you very much. I'm just envisioning the first road crew that's both human and autonomous on the moon, how that will work.
Hopefully I'll be there to watch them.
Great. I'd like to now move on to the next presentation. In addition to being the 50th anniversary of Apollo 15, this is the 75th anniversary of the Space Physics Research Lab here at the University of Michigan. And delighted to introduce to you Pat McNally, who's the Managing Director of SPRL, also a University of Michigan engineer. He got his start at JPL and then worked in a number of other industry settings before he found his way back to Ann Arbor. And he's going to tell us the story of SPRL. It's all yours, Pat.
Thank you, Mark. That's a tough act to follow. Two very good presentations so far. Looking forward, I'm going to look back a little bit first. And I'm going to start with a video that was just produced, and you can watch it on YouTube again. I have the link in the end of this, but I'll be quiet and you can listen.
It was very exciting, to be part of something new, growing, exploring things that have never been explored before.
The Space Physics Research Lab here at the University of Michigan. It was founded to study the upper atmosphere.
SPRL originally was basically an instrument builder and flyer. The early 60s when space exploration expanded very significantly, and SPRL was a part of that expansion and had an excellent reputation.
Originally, they were looking at rocket projects, which launched kind of sensors to measure the upper atmosphere and to understand it. Over time, it evolved. It's all about highly reliable, autonomous systems that go to extreme places and can survive for tens of years. SPRL engineers work on a really wide variety of projects. They can build sensors to put out in the ocean to measure waves and winds and things like that, or they can build sensors that go out to the far reaches of the solar system.
SPRL has built a large number of instruments that have gone to Jupiter, Saturn, Mercury, and Mars. And we've built and flown a number of instruments that look at the sun.
Being situated in the university is ideal for SPRL. It's this great educational experience. Everyone is learning. We've got students that are coming into SPRL. They're working on these projects, these one-of-a-kind space missions. They're learning directly from engineers who are, they're not just designing one little widget, on a car or, on an airplane. They're designing something that is one of a kind and it's going to go to space. It's going to launch. We're really focusing on sustainability going forward. How do we sustain the lab, sustain the research community by helping people achieve their engineering goals and their scientific goals?
So I hope that came through okay. I am going to elaborate on some of the themes that were presented there in the video. And actually go back to the beginning. I will start by saying that getting to space takes hardware, it takes software, and it takes people working together as a team. And as a University of Michigan alumni, you might call this presentation, the team, the team, the team. For 75 years, the SPRL team has been getting people to space with their eyes and ears in our instruments. Let me take you back and tell you how it all started. So remember these vacuum tubes. In the early days of electronics, they were essential electrical amplifiers for radio signals, for musical instruments. SPRL started with an innovative idea. The innovative idea came from William Gould Dow, a professor in the Department of Electrical Engineering at the University of Michigan. Professor Dow used his deep knowledge about electrical circuits and vacuum tubes to reason that the vacuum of space, with an appropriate cathode, anode, and other electronics, would form a measurement system for the charged particles of space. Space provides the vacuum, and the circuit collects and counts the particles. The year was 1946. The U.S. Army had captured V-2 rockets, and together with the U.S. Navy, a joint research program was started to use these rockets for upper atmosphere research. At the time, the structure of the atmosphere was a big unknown, but Dow knew from his World War II experience that the atmosphere affected radio communications and the trajectories of rockets. The US military funded Dow's idea, and he became a member of the V2 Upper Atmosphere Research Panel. Dow's team designed an instrument to measure ions in the atmosphere based on the principles of the vacuum tube. Dow provided this eyewitness account years later of the first University of Michigan instrument flight attempt on a V2. Our first V2 was launched on time. I was in the blockhouse. By the time it was 50 feet in the air, it was tipped at 30 degrees from the vertical. It leveled off at 300 feet altitude, flew a mile, and dove into the ground. Great was the fire thereof. So the engineers at the time got back to work, this time understanding everything they could about the rocket systems and instrument integration. Soon the team was ready for their next attempt, a success. And since that first success, the lab known as SPRL has developed 34 successful sounding rocket launched experiments, over 45 major space instruments, and over 60 aircraft and balloon launched experiments. But this presentation is not about the numbers. This presentation is about the people of SPRL through the years and the innovative instruments they developed to support the research program, the U of M, and the nation. As SPRL was successful in the early days, Dow realized he needed to build an innovative team that could build more instruments to measure the upper atmosphere, instruments that work to higher altitudes, instruments that would provide more accurate and complete data. Dow recruited a key member named Spence, who Dow knew as an undergraduate student, who could make, as he said, anything work. Spence was Nelson Spencer, who joined Dow in mid-spring of 1946 and soon became responsible for all launch preparations and field activities. In the early 50s, Nelson Spencer became the director of the now named Space Physics Research Laboratory. Spencer was a hands-on director, working directly with the team that he built up. And you see him working on one of the sounding rockets here. He built a strong team, often recruiting electrical engineering students to help. Here's a picture of some of the SPRL team in the 50s with Spencer here at the bottom right. This team included 3 future directors, Larry Brace, George Kerrigan, and Andy Nagy, who you saw in the video, and 2 key staff members for 4 decades, John Maurer, and I'll talk about him, how he mentored many other engineers in the years to come, and Lyle Slider, who actually taught me how to solder when I was a student in the 70s working in the SPRL lab. What I want to talk about in a little bit detail, though, is this probe that was in the middle that George Kerrigan was holding on to. Now, it wasn't colored red. An artist did that to give it some emphasis. This dumbbell probe is what I want to talk in some detail about. From the early measurements made with a rocket-mounted ionization probe, the team discovered a problem with the instrument data before the dumbbell probe. The rocket itself was contaminating the measurements through rocket exhaust gas and off-gassing, so the idea was to separate a free-flying probe, eventually known as the dumbbell probe. The satellite is 2 6-inch diameter spheres connected by a 12-inch long, 3-inch diameter cylinder. The gaps shown in the various sections of the dumbbell are electrical insulators. We have one of these probes in our cabinet here at SPRL today. If you look closely, you can see it behind me. Here's a simple block diagram. You sweep the voltages on the 2 ends of the dumbbell, and that would alternately attract ions and electrons to the detectors, measuring the ionization of the atmosphere. The dumbbell was a free-flying, self-contained scientific probe with attitude measurements, batteries for power, and communications equipment, all to support the ion and electron measurements. This is where I lost you. We launched these things at Fort Churchill and then at Wallops. And in the early 60s, Nelson Spencer left SPRL. And right after NASA, within 2 years of when NASA was formed, and he went on to NASA Goddard to become the chief of the Laboratory for Atmospheres. And he continued to support SPRL research, which was very significant, and bring some of the university's top talents to NASA. So not only did he help us, he took away some of our key people in the years to come, but they stayed friends of SPRL. So let me try to get back on track here a little bit. One of those persons was Hasso Niemann, who began the age of space-based mass spectrometers. And here's some of the early documentation from something called an Omegatron. It was an early mass spectrometer that didn't turn into a very good design. It was eventually replaced with a quadrupole mass spectrometer. But there's many elements of this Omegatron that are very much like the mass spectrometers we use today. And the key thing, and I didn't show you earlier, the person that wrote all of these drawings and signed off all these drawings with Hasso Niemann was John Maurer, who now became the chief engineer at Space Physics Research Lab in the 60s and worked across a number of projects. Here's Hasso Niemann. He was a founding father of atmospheric experiments and mass spectrometry. And he is standing here with the Galileo mass spectrometer, which went into the Jupiter atmosphere. His work ultimately led to the successful SAM experiment currently on the Curiosity rover, and I'm going to talk about that. To make up some time, I'm just going to go through quickly some of these early mass spectrometers. A key aspect of them is this high voltage section. Back then, it would generate hundreds of volts. Now we generate thousands of volts, and we're working on these types of power supplies that generate hundreds of thousands of volts and more. Another key engineer in the beginning was young Bruce Black here. This is a dynamic explorer experiment that was built by George Kerrigan and Bruce Black and team. All right, I'm going to click through these quickly. So I went to JPL, as Mark said, and I actually worked on the Galileo probe that carried the SPRL developed gas mass spectrometer. And it sits inside this probe and got dropped into the atmosphere. I was part of the probe relay link team, among other duties there at JPL. Here is the final electronics assembly. So fairly compact. This is the start of the era of digital electronics. You see a lot of analog electronics, but you also see digital electronics coming into the instrumentation now. All right, so now I think I'm about back on track here. And I want to go back a little bit to the Apollo 15, the event that we're celebrating today. It featured the first lunar rover. The Apollo team came up with the creative idea of a rover to get around to the various sites of interest. And a number of innovations were built into the rover, including the special tires and electric drive system. Astronaut Scott was the daring driver. We talk about in the College of Engineering, creativity, innovation, and daring. And so we see the creativity in the rover, we see the daring in the driver, and we see the innovation in what was developed to drive around on the moon. So in the spirit of all of this, we try to continue that today with our team. Astronaut Irwin likened riding in this thing to a bucking bronco. So I can imagine astronaut Warden here on the right, looking down from above on the first interplanetary dream cruise, like the famous Woodward Dream Cruise we'll celebrate 2 weeks from now in the Motor City. So in the same way, the SPRL team has been creative, innovative, and daring in the instrumentation. This is the Curiosity rover, where there's a key instrument that was developed by SPRL on this. And now recently, the Perseverance rover also has SPRL instruments. So NASA Goddard and the SPRL team developed the ultimate planetary mass spectrometer to date, and that's sample analysis at Mars. For 9 years, SAM has collected, analyzed, and stored samples for in-depth investigations paving the way for Mars Perseverance, and the SPRL developed Pixel and SuperCam instruments. A key part of the SPRL team is the mentoring from one generation to the next. Here are three incredibly talented high voltage engineers: John Maurer, recruited by Nelson Spencer; Steve Patel, who worked in the lab in the 70s and the 80s, and then went on to form his own business, Patel Engineering, and impacted a number of instruments and satellites since then. And then Ken Arnett. So three generations of incredibly talented high voltage engineers that have pushed each other and learned from each other. And this continues today with Ken Arnett and Steve continuing to mentor new engineers in our lab. So I want to talk about, as Sue Laprie talked about, we measured the atmospheres in the early days, and now we measure the atmospheres on other planets. We measured the winds. Mercury Messenger measured winds of another kind, and that is the solar wind and the interaction with the magnetic field around Mercury. So in order to do this, the FIPS instrument was developed, a very compact instrument. You see it next to a 1-foot ruler here, but inside quite a bit. So this is the FIPS instrument construction. It utilized the digital conversion approach to measure particle transit times in the time of flight section here. Expanded, so the particles flow into the device, particles flow into the device, they get shaped by electrostatic analyzer section. They come into the time of flight section, and then they trigger the detectors, and the electronics count the number of particles that hit, as well as where they hit on the detectors, so they can determine what kind of particles were absorbed from the solar wind or from the trapped magnetosphere around Mercury. FIPS was very accurate in doing this. It could distinguish between a helium +2 peak, which is very close to a hydrogen +1 at its highest energy. So FIPS was a very accurate instrument. I mentioned it utilized a unique digital conversion approach to measure particle transit times. And it really expanded the SPRL expertise in measuring velocities, compositions, and densities now, including ion densities on other planets. So some of the people involved in this, Dr. Jim Raines, who still collaborates closely with us on a number of projects in SPRL. On the other side, you might recognize Professor Thomas Zurbuchen, who was the principal investigator of FIPS and now is the NASA Associate Administrator for Science, and Steve Vergacki, a key engineer in our lab that developed the digital electronics on the FIPS instrument. So some of Steve's work later received a patent for his time in digital FPGA design that was inspired by the FIPS instrument. And he continues to work in the lab today, developing new designs and mentoring students and young engineers. Sue Laprie mentioned Solar Orbiter. In fact, they were at the launch for Solar Orbiter. And this is a little bit more information on the heavy ion sensor on Solar Orbiter that was developed with Sue and the SPRL team. All right, so come up to present day, including SOHIS and Cygnus. Cygnus came out of a bold idea from Chris Ruff. Professor Chris Ruff had the idea of a very different way to measure ocean winds from tropical cyclones, utilizing the global positioning system with a sensor that measured Doppler interference. Professor Ruff imagined a system that would look through the storm clouds and torrential rains and measure the reflection from surface waters to determine wave intensity. So his Cyclone Global Navigation Satellite System was selected in the Earth Venture Program in June 2012. And to achieve Professor Ruff's bold idea, the SPRL team was given several specific challenges. First, a method to prove out the end-to-end signal processing chain of the complex system was needed. The method should compare direct and reflected GPS signals into a realistic signal scenario that could be processed through the receiving antennas to feed the delayed Doppler mapping instrument. This was needed to prove out the instrument and the spacecraft signal processing. This task was taken on by Bruce Block, who we talked about earlier. Second challenge was developing the science data processing software that could take the instrument data in the form of these delayed Doppler maps, perform very complex correlations, subsamples, calibration adjustments, and GPS spacecraft attitude and location adjustments to come up with level 1 data products and eventually gridded wind speeds. And this was done by a team of software programmers who I'll show in a minute. And the final challenge was a rapid development of qualification of magnetic rods. The supplier that was to deliver these magnetic rods went out of business just prior to flight fabrication, leaving the project with no way to deliver a key actuator for spacecraft attitude control. SPRL team, Steve Rogacki in particular, took on the flight actuator development, moving quickly from prototype to flight hardware of 32 torque rods within a period less than 6 months, which is just about unheard of in the space business. Here's the 8 Cygnus satellites integrated on the launch adapter from Sierra Nevada. And here is the Cygnus team with 2 of these magnetotorquers on the vibration table. Dr. John Van Noord was responsible for the vibration certification as well as the thermal modeling and validation of the Cygnus. And you see a number of the Cygnus SOC team, software development, hardware development, system engineering, fabrication, machining, and science in this picture. So I want to talk real quickly about the road ahead. And so we can look to the past to understand some of the challenges we might see in the future. And the future doesn't belong to the faint-hearted, it belongs to the brave, as President Reagan reminded us after the Challenger accident in 1986. This was the event that gave me pause to come back from JPL to Michigan and start my young family here. We're reminded also that the Apollo program had its own tragedy when Michigan native Roger Chaffee and Michigan alum Ed White also died tragically along with Gus Grissom in a pre-launch test on Apollo 1. But I see a new day ahead. Humans returning to the moon and to Mars, a day of...
Langley, Glenn, Ames, doesn't matter.
Yeah, no, I really don't.
So I see returning to the moon, returning to Mars, a day of reinvigorated planetary exploration and looking outside of our solar system, as Dr. Warden talked about earlier. At SPRL, we'll continue to do what we have done successfully for 75 years. We'll take on daring initiatives. We'll collaborate as a team with our fellow researchers and faculty with the University of Michigan, Space Institute, NASA, and industry. And we'll build the team of the future through hands-on, experiential learning and mentoring. The seeds are now planted in areas that will guide the next decades. An example is here, some of the radiation protection technology that we're developing. We know that we're going to find life on other planets. It will be us. We'll be on Moon, we'll be on Mars, and other planets eventually. To protect life on the journey, we're developing protective radiation shielding technology with NASA, JSC, and JPL. It's active technology that can be turned on when there's a solar energetic particle event and powered off to recharge its power. So we're testing this system in the lab now, and especially interested in the plasma effects on the shielding capability. And so we've proven out with JPL and JSC that shields can be developed, but we also know that plasmas can dampen the effectiveness of these shields. And so this is testing that's going on today in SPRL. This is also equipment that we put together for the high voltage testing at Brookhaven National Labs, where all of our high-powered radiation protection testing goes on right now with JSC and JPL. And you see Ken Arnett here mentoring Eric Vigis, the next generation of development of high voltage systems and vacuum systems. We need a lot of power in space, and so we looked at, can a Pelletron supply the current for a radiation shield? We happen to have at the University of Michigan, right across the street, the Michigan Ion Beam Labs facility, which contains Cockcroft-Walton amplifiers, just like we use in Pixel and in our mass spectrometers, as well as a Pelletron that gets driven by that Cockcroft-Walton amplifier in order to charge the beam system. So a Pelletron is a way to develop high currents that may be needed for future space missions. I want to also talk about the search for life that, again, Pete Warden talked about earlier. Dragonfly, a very exciting project with APL and NASA Goddard, will also bring a mass spectrometer developed by SPRL and Goddard to the surface of Titan. And the overall mission will be led by a U of M and SPRL alumni, Peter Bedini. So not only do SPRL alums like myself come back to SPRL, but we also go out and do great things like Thomas Rebuke and Peter Bedini and many, many others, and Steve Patel. The future is bright for SPRL. Here is a collection of the projects that are current and we expect to be funded very soon in a number of areas. We'll continue to understand, excuse me. So with each of these areas, we look at how do we fit into the bigger picture? How do our teams support the large initiatives that we have as a nation and as humans? So all these are part of our greater yearning for understanding as we explore our solar system and beyond. They're listed as part of these bigger initiatives and the bigger teams that SPRL and the U of M supports. So protecting our planet, living with a star, our sun, search for life, human space exploration, and building on also what Dr. Warden talked about, looking beyond our solar system with a facility that's being developed to test and characterize IR sensors to be used in exoplanet searching systems of the future. Here's our staff today. I just want to acknowledge that it takes a team, and it's an incredible team to work with at SPRL, incredibly diverse and exciting team to work with, and experienced, and those gaining experience daily working with our chief engineers and lead engineers. Just three of the logos through the history of SPRL. And with that, Mark, I'll turn it back to you.
Thank you very much, Pat. We are now going to move on to the next presentation from a long-running and successful student team called Bioastronautics and Life Support Systems, or BLISS. And I see Chad on, and Catalina. Go ahead and take it away.
All right, sounds good. Yeah, can you see the proper screen?
Yep.
All right.
Can see it.
Perfect. Let's go into that. All right, so hi everyone. My name is Chad Cerruti, and I'm also joined by my co-lead and friend Catalina Garza. Thank you for coming to the Bliss presentation for the Apollo 15 50th anniversary celebration. We're really excited to celebrate this moment in history for spaceflight and talk a little bit how Bliss is pushing human spaceflight forward and continuing to advance the ways that we think about humans living in space. So, who is Bliss? What do we do? Historically, we were a part of the NASA XAB Challenge, where we'd work with various NASA centers to help solve various problems in human spaceflight. We consist mainly of graduate and undergraduate students from a whole variety of majors and disciplines. So we have a true interdisciplinary team that's able to come together and solve these complex problems. This year, we're actually diverging from the XAB Challenge, but we'll touch on why later. It's a part of a series of changes we're actually making to the team. But so in the past, some of the challenges that we've solved include turning human wastewater into nutrients for plants, designing and constructing like a full-scale mock Mars habitat that we actually still have in our workspace, 3D printing soil for plants, and creating cutting-edge user interfaces to advance the ways that astronauts can interact with their habitats in space. And so touching more on those those interfaces, we're excited to share some of the research that we performed last year involving a voice-activated user interface to give you an idea of how the team approaches a problem, works through our challenges, and develops solutions for astronauts. And so for 2021, our objective was to design a unique, efficient, and intuitive voice management system for autonomous operations on the Lunar Gateway for crew interactions. It is a mouthful of an objective, but essentially NASA wanted us to develop an Amazon Alexa or a Google Home system with a couple key changes that an astronaut might be able to use to interact with the space habitat system. And additionally, for some of our own internal goals, we wanted to try to make our voice user interface as human-like as possible. Through some of our preliminary research, we found that users develop a stronger bond and a greater trust with the system when it feels personal to them. And so the best way to do that was making our VUI feel like another member of the crew rather than like a robot assistant. And this would also encourage the astronauts to fully utilize the VUI and use it more, which would in turn increase the VUI's usefulness. And so accomplishing this, in addition to giving our VUI a name, which is Diego, and having them talk human-like, we wanted to also make sure the VUI was able to quickly understand information, as well as understand multiple ways of saying the same thing and accessing the same data like a human would. Also supporting the astronaut, we wanted to include a graphical user interface to increase the accessibility for the system, because while getting directions read out to you by a voice is really helpful, there are some situations where using a screen is just better. And then finally, the ISS is a very noisy environment, and we anticipate future space habitats to be similarly pretty loud. So we looked into methods of reducing the background noise. I don't know if anyone's ever used an Amazon Alexa at a party or in a noisy situation, but you know how frustrating it can really be for Alexa to properly hear you. And we want the astronauts to think of Diego as a friend and a crewmate, not as an old person losing their hearing.
To give an overview of how our Diego system works, moving from right to left across your screen, the astronaut begins by stating a command or question, such as, "Hey Diego, what's the temperature?" This command will be picked up by microphones, sent to the system, where it's converted into a string of text that the natural language processor can then interpret. Then a request is generated and sent to the vehicle system manager to perform an action or get some information. Information is then sent back to the user through audible and visible displays. Every step in this process, from how the user asks a question to how the system interprets and pulls information, was vital to our project. So we'll go more into depth about each of these pieces. Starting with Diego, we wanted to research various traits a voice assistant should have. So we sent surveys to students in our group, other students, faculty, and young industry professionals to understand what members of the Artemis generation think a voice assistant should act like, as they'll likely be the astronauts in the coming decades. We then tried to decide on a person that might fit those traits, and that's how we came up with Diego. Diego is a 39-year-old male from the coast of Spain with multiple STEM degrees who loves his family, the outdoors, and astronomy. It seemed a little cheesy at first, but it honestly made the next phase of development a lot easier. And that's where we created our dialogue paths. With Diego in mind, we wrote and designed the conversation paths a user would use to interact with Diego and make the process as natural as possible. We didn't want the interaction to feel robotic, so we wanted to add some personalized responses that only Diego would really use. As for the information available to the astronaut, we chose 4 categories that could benefit the most from a VUI interface. Those categories were station vitals, communication, scheduling, and tasks. Station vitals refers to all the points of information about the station. Communication refers to interacting with other astronauts over the microphones, as well as ground support. Scheduling refers to managing what activities an astronaut has to perform throughout the day, being able to rearrange them, and setting reminders for each of these tasks. And task refers to the process of completing a task, including reading step-by-step instructions and manuals. The standard conversation would go something along the lines of a user asking a question or stating a command. Diego would respond, confirm with the user verification, and the system would answer or act. One of the main features of our conversation design was making sure that a user could state the same question multiple ways and Diego would understand them, as well as allowing Diego to respond in different ways to make this system feel more human-like. Integrating these conversation pathways into hardware and software took quite a few pieces of tech. The most important being RASA. As you can see on the right of your screen, RASA is a natural language processor that attempts to understand a user's intent through the questions it is sent. Using AI modeling, RASA can fill in some of the gaps that users tend to leave when they speak to other humans, expanding the ways a user can ask a question. This has the dual benefit of allowing astronauts to converse more casually and fluidly with Diego, as well as keeping our coding and implementation fairly simple. To explain the rest of the system, with a typical scenario, the user will activate the system by stating, "Hey Diego." The user then states their command or question, such as, "What is the temperature?" And this is passed to our speech-to-text translator, Mozilla Deep Speech. This new text gets passed into RASA for interpretation, and a request is sent to the Vehicle System Manager, NASA's NPAS system. NPAS stands for NASA's Platform for Autonomous Systems. Information is pulled from here and relayed back to the user through Diego's voice and potentially a graphical user interface display. And so we do have some demonstration of Diego in action. Due to some of the limitations, we focused on system vitals category, specifically for this demo, and laid the groundwork for NASA team to further implement other categories. Additionally, we were unable to find a suitable male voice for an output. In the future, we'd probably hire a voice actor to truly capture Diego. So we ended up going with a female voice that we actually called Dora for this demonstration. This entire project was based on the idea that we would conduct trade studies and perform research for NASA's team so that they could implement and construct their own VUI. So the fact that we actually have a working demo is beyond the initial scope for this project, and we're extremely happy at our product. So here we go.
I probably didn't share with sound. Hold on, let me redo that. There we go.
Hey, Diego.
How may I help you?
It's nice to meet you.
It is great meeting you.
Hey, Diego.
How may I help you?
What is the temperature?
The temperature in the habitat module is 21.15 C.
Hey, Diego.
How may I help you?
What is the pressure?
The pressure in the habitat module is 100.57 kPa. PA.
Hey, Diego.
How may I help you?
What is the pressure in Pascal?
The pressure in the habitat module is 101.11 kPa.
Hey, Diego.
How may I help you?
What is the pressure in Pascal?
pressure in the habitat module is 101,110.0 Pascal.
Hey, Diego.
How may I help you?
Goodbye.
See you later.
So that was Dora, and obviously you can see there are some quirks to the system, such as not recognizing words and commands. Most of that is relatively straightforward for NASA team to iron out through using RASA by implementing an addition of common terms such as Pascal and linking the phonetic pronunciation. A lot of these slip-ups can actually be solved, and he or she can be more lifelike.
We don't need to listen to that again. Okay. And finally, we looked into the background noise and mitigation for part of our project. Like I mentioned before, the ISS is a very noisy environment, and it's primarily due to the ECLIS system constantly cycling air, water, coolant throughout the station. We anticipate the Lunar Gateway and other future space habitats to be pretty equally as noisy, but since voice user interfaces don't work well in noisy environments, we had to look into multiple methods of reducing that noise. We studied both active and passive methods of noise reduction, with active noise control using speakers and microphones to monitor that noise level in the environment, and then sending out canceling sound waves to help reduce noise levels at both the microphone level and for the astronauts, as well as passive noise control, which used soft materials such as foam to absorb some sound waves. And overall, we'd hoped to reduce the noise on the station by about 20 decibels, which is pretty significant, but we were pretty successful in doing so from our testing. And so from some of our passive noise cancellation testing, we were able to reduce higher frequency noises by about 20 decibels at around 4,000 hertz and above for noise frequencies. And then combining this with our active noise cancellation, which works much better at those lower frequency registers that the passive didn't capture as well, we showed that it actually is entirely feasible to reduce the noise on board the station to the point where it's effective for a voice user interface to work on board a space habitat and be useful. And so just to summarize again, we worked on a voice user interface named Diego that will allow astronauts on board the Lunar Gateway to interact with the system using their voice. We designed Diego to be human-like, and we're able to accomplish this through conversation design and software such as RASA. We also leveraged a GUI to increase accessibility to the system. And this entire interaction will be possible because of the background noise research we've conducted. As part of our research, we did a lot more than just that demo shown. We have full conversation paths for each 4 of those categories we mentioned above, written out with multiple responses from Diego. We have a whole personality and trait list set up for Diego so that the NASA team understands who Diego is as a person. They were on board with keeping Diego as the personality for the station. So that'll continue on, and we're happy with that, as well as a whole user interface manual that they can use to properly set up Diego and all of the hardware and software we developed on their own systems. And so for 2021, 2022, this upcoming school year, what do we have planned? Like we mentioned before, we're not participating in this year's NASA XAB Challenge, and instead we'll be working on our own project. And for this year, we decided to work on autonomously setting up and disassembling a large-scale 3D printer on the lunar surface with minimal human intervention. So Dr. Hilberger, we would love to talk to you more about this. After hearing your talks, we're really interested. But so a lot of companies that we've seen, and entities too, they're working on the 3D printing structures either here on Earth and plan to send them to space, or they're working solely on a space-based design to build structures on the surface of the moon. But when you look at all of these companies and the promo videos they put out, they always seem to cut from when the thing is in space and when it's fully deployed out on the surface. And we want to try to target that area and take it from, oh, we're not going to worry about that right now, we're worrying about our own printer, and actually put that into action. And so some of the areas we want to actually solve are deploying the printer from whatever its flight configuration is, and maybe figuring out that flight configuration as well, preparing both the terrain as well as the building platform for the printer to begin, and then potentially removing the printer after it's completed its build. And so we intend to research these ideas, as well as then build our own scale model of a printer that's able to go into a flight configuration and then deploy, and possibly some of the scanning and preparation as well. And so as the leads for the project right now, the project will begin at the start of the school year. So this is still the preparation phase. We don't have any research into it, but we're trying to right now find a 3D printer design that we can use so that we don't have to come up with our own idea in our own 3D printer. That's not the point of this project. We believe it'll be more beneficial, especially if we can partner with a company on this, because it will give them direct benefits to their company and it will give us a 3D printer to work on. We don't need to waste our time. And so just to talk a little bit about the types of printers we'll go with, depending on who we end up working with or who we find, there'll be one of two types. The first is one of the standard printer designs that they typically use here on Earth. That icon video that Dr. Hilberger showed uses specifically. It's pretty similar to how they print using plastic here on Earth, where they have kind of like 4 corners set up and you print inside this build design with a 3-axis nozzle, and that's on the left side of the screen. But then the second and potentially more useful and more relevant for space printing is this radial printer design, which you put it in the middle and then it prints in a circle around the printer and prints kind of up and over. And that's potentially better because it's usually a smaller footprint. It's a lighter weight printer. And those rounded habitats are typically what also space habitats are proposed to look like. But all of this is a work in progress right now. And many of our answers are going to come from the research performed during the school year. But we're extremely excited for this project and cannot begin work on this. So, and then additionally, one of the last things that we're doing for the project is we want to try to expand the scope of the BLISS project and what it is right now. So right now we're just a project team on campus and we are very good at that. We've been working since 2013 on various NASA projects, but we really feel like there's a gap and a niche that we want to fill here on campus for all the enthusiasts for space habitation as well. And so one of the first steps we took towards trying to become more of a organization that celebrates space habitation in general and is very enthusiastic about it is we updated our logo. You might have noticed in the top right, we had it there, but we really wanted a new logo that would emphasize our current and future outlook into space habitation. So within that logo, you can see coming off of the B is a representation of the International Space Station and where space habitation currently is. And then on the right side of the logo, coming off of the S, is a more Jetsons-esque futuristic space station that'll be in the future. But aside from that, one of the things we really want to do is try to collaborate a lot more with some of the other organizations on campus to increase awareness for BLISS, and then also try to create a community of space habitat enthusiasts. For this current upcoming project, we want to work with the 3D Printing Club on it for obvious reasons, as well as the CLAWS team on campus, which does a lot of visualization in CAD work and such, as well as get more involved with SEDS here on campus, which if anyone doesn't know, SEDS is a great organization, the Students for the Exploration and Development of Space. It's a large network of space students and we want to try to tap into that as well. In addition, we want to try to connect our professors and companies that have signed on to support BLISS with all of the members of the BLISS team outside of just a purely professional standpoint and have some more networking events and casual events and maybe have them give some talks throughout the school year and things like that. We also, as any company trying to grow in the 21st century has to do, we want to try to increase our online presence and grow our social media so that not only the University of Michigan, but anywhere around the world, if they find our page, can learn a little bit more about space habitation and the work that we're doing. But yeah, thank you so much for listening to our talk about the research that we've done in the past and are continuing to do in the future. I also just wanted to give a big thank you to our PI, Nilton Reno. He is phenomenal. He's he supports us in so many ways and gives us a lot of freedom to really work in the ideas and such that we really want to pursue. So just thank you to that. Thank you to the rest of the BLISS team too, that makes all of this work and research possible. Yeah, thank you so much for listening, everyone.
Thank you both for the presentation about your future activities, and I'm glad you connected with Mark. It sounds like he would be a great resource. I'd now like to go to our last presentation. Dr. Ben Jorns is an assistant professor in aerospace engineering and also the co-director of the Pebble Lab, which is the plasma propulsion lab here at the University of Michigan. He did his undergraduate at Yale and his graduate degrees at Princeton before going out to JPL as well. And we're fortunate to be able to recruit him to the University of Michigan a few years ago. And so, Ben, it's all yours.
Okay, thanks, Mark. So I wanted to spend my time today talking a little bit about some of the technologies we've been investigating and to try to push the envelope forward in expanding humanity's reach out beyond the Earth-Moon system. And our specific focus in my research group is developing next-generation propulsion technologies that should make that region a little more accessible. You can see here on the left-hand side an example of one of these thrusters that we're working on, and I'll talk about that a little bit later. I think to relate it back to the theme of this symposium, the Apollo 15, of course, represented a culmination in technological innovation. The entire Apollo program did, and is in large part due to significant technological leaps forward in a very brief period of time that enabled us to access the moon and to do kind of this novel space and exploration. But to give some context to the problem that was faced by the Apollo engineers in that decade, if you look at the problem of reaching the moon in terms of distances and length scales, at the beginning of that decade, 1962, the farthest we had made it from the surface of the Earth was about 150 kilometers with the Mercury program and low Earth orbits. And that was enabled by more or less adapted rocket vehicles that were based off of ICBMs. But the challenge that was put to us in the early 1960s by then President Kennedy, of course, was to reach the moon and actually land humans on there. And you can see the challenge of this is captured just in terms of the disparity in length scales. We wanted to extend our reach by a factor of 1,000 beyond where we were at the beginning of the decade. And of course, faced with this challenge, the issue became, can we develop technologies that will allow us to make this 1,000-fold leap forward beyond the surface of the Earth? And of course, when you have at your disposal a 0.5% of the or 5% of the budget of the U.S. government and GDP, and a workforce of thousands of engineers at your disposal, as Pat alluded to earlier, through the development program that were in part sponsored at SPRL, you can advance technology quite rapidly, and we can go from these 28-meter tall rockets to ones that are 100 meters tall, or about a third the size of a skyscraper. And indeed, the culmination of this technological development program was the Saturn V, the most powerful rocket ever built, which in turn enabled us to expand our reach from this 150 kilometers, a 1,000-fold outward to ultimately reach the moon. So that gives some perspective on the kind of technological innovations that were required for propulsion in order to achieve this objective. And that brings us up to the present day, where we're starting to set our sights farther, where our current record in terms of distance from the Earth, at least for crewed exploration, is this 380,000 kilometers. But now we're setting our sights even further, going all the way out to Mars. And so the question becomes, what kind of technological innovations are necessary to extend our reach by, again, a factor of 1,000 to reach Mars? Does this kind of program require that we have an innovation on the length scales or the size scales represented by this disparity between the Mercury Atlas and the Saturn V, or are there other technical paths and avenues available for us to try to make this leap forward? So, of course, I'll caveat with that saying that robotic missions can, in fact, reach Mars, and they can do that with rockets that are smaller than this record-setting Saturn V. But that ultimately stems from the fact that the payloads that we send to Mars, while increasing in size, are still limited. The Mars Science Laboratory, for example, is about the size of a Volkswagen Beetle. However, the problem becomes exponentially harder when we talk about crewed exploration. And to give you a sense of scale here, here's an example of a crew transport vehicle that's been proposed by NASA that would be necessary to send a crew of 3 to 5 astronauts to Mars with sufficient consumables on board and propellant on board to brake and to support those astronauts for a 9-month to 1-year-long journey. And you can see for scale here, the Mars Science Laboratory shown drawn up against it. And this really underscores the fact that in terms of propulsion and technological innovations, making the leap forward from the moon and beyond to the Mars becomes an exponentially more difficult problem when we transition from robotic-based missions to ones that are crew-based. So of course, the challenge, the one that inspires us in my research lab, is trying to develop technologies that can address this technical gap and this very real gap in terms of distances. And of course, one brute force approach would be to develop increasingly larger launch vehicles. The idea being that we could launch, as we did with the Apollo program, a spacecraft directly to the moon. But of course, you apply the same kind of scaling laws that went into the development of the Saturn V, scaling it upward from that Mercury Atlas rocket that supported John Glenn and the Mercury astronauts in low Earth orbit. You come to the conclusion that we're going to need prohibitively large rockets, ones that are approaching the size of the Empire State Building. So the kind of question becomes, from an architecture and technology planning perspective, what kind of propulsion innovations and technological and architecture innovations can we motivate to try to make this crewed exploration of Mars more accessible? And of course, one strategy that's been landed upon is, instead of doing a direct launch from Earth to a Mars transit orbit, we could instead adopt an architecture in which assembly is done on orbit. And we heard some talks a little bit about infrastructures earlier today. And in broad strokes, the architecture is shown here, in which you have crewed vehicles that provide consumables and establish the base on Mars. And then you have a crewed vehicle as well. The central idea or concept being here that you use these limited launch vehicles to send up payload, assemble it in orbit, and then that vehicle in turn transits. So in practice, this is, of course, thought to be achievable. This is a design reference mission, which is released by NASA about 10 years ago, design reference mission 5.0, and it's thought to be done with the types of launch vehicles that are available now or will be in the near term. But of course, in practice, one of the major challenges is that in order to support a crewed transferred vehicle, the mass of that overall assembled vehicle can be prohibitive. And as you can see here, it can lead to a requirement for increasingly large number of launches. In this design reference mission, we have 4 launches. Whereas the more launches you have, the higher chances of failure and the more complexity for assembly on orbit. So one of the approaches that we're exploring in my lab is trying to identify strategies in which we can reduce the propellant of that transfer vehicle, or reduce the mass of that transfer vehicle. And indeed, the approach stems from the fact that propellant is one of the major mass drivers for these transfer vehicles. The propellant required to get from low Earth orbit to Mars for these vehicles can be prohibitively large, and can in fact represent the bulk percentage of the overall vehicle mass. So the prevailing thought here is, if we can identify innovative propulsion strategies that use propellant more efficiently, it lowers the overall mass of the vehicle and enables crew transport architectures that can be faster and more economical. So this kind of sets us up for discussing the focus of our lab, the Plasma Dynamics Electropropulsion Laboratory, which is to identify the technologies that can enable this kind of next generation architecture. And you can see here on the left-hand side a view inside the vacuum chamber in our laboratory, in which we have a wide range of the advanced generation technologies that we investigate. And the lab group is shown down here on the right-hand side. PEPL has actually been an institution at NASA for the past 25 years and has had widespread influence in the field in terms of developing next generation technologies, with a number of our alumni going on to positions at NASA, JPL, Glenn, and the Air Force Research Lab. And indeed, the overarching theme of our approach is to identify, again, these technologies that enable more efficient and rapid transfers in space to support both efficient robotic crewed exploration, as well as, I mentioned earlier, crewed exploration. So the prevailing technology that we research in the lab is so-called electropropulsion. And the reason why we go after this is that it has the potential to enable orders of magnitude reduction in the propellant mass required for these crewed architectures and transfer missions. So I want to talk a little bit about what the nature of this technology is and why it can enable these orders of magnitude reduction in propellant. And then I'll highlight some of the problems in the context of this, this challenge of enabling crewed exploration to Mars. So in broad strokes, electropropulsion is directly the analog to the terrestrial transport, where on the left-hand side, you have more traditional chemical-based or combustion-based vehicles that rely on gas, combusting gas to move forward. And on the right-hand side, you have all electric vehicles. And as we now know intuitively, electric vehicles can get almost an order of magnitude higher miles per gallon equivalent compared to their more conventional counterparts. So too is the case for our so-called electric propulsion vehicles, whereas on the left-hand side, you have a more traditional chemical rocket. On the right-hand side, you have an electric propulsion vehicle. And in the same sense, electric propulsion vehicles in space can offer orders of magnitude reduction in the required propellant, or effectively a higher miles per gallon to traverse deep space distances. So let me take an aside here and just say a quick word on why EP has this improvement in capability over more conventional chemical rockets. And to do that, let's contrast the principle of operation of a chemical rocket compared to an electric propulsion system. So I'm showing here on the left-hand side the principle of operation of a traditional chemical rocket, in which an oxidizer and fuel are combined in an upstream combustion chamber. They're combusted, and the heated propellant is then expanded downstream through a converging diverging nozzle. This ultimately leads to the acceleration of the propellant and the generation of a reactionary force in the opposite direction. Now, the key underlying principle of operation lies on the release of chemical energy stored up in the bonds of the oxidizer and fuel. And this is a very expedient way to release energy, because it's already handed to us in the form of these chemical compounds, which are readily available. But this expedience in turn kind of leads to one of the limitations of a chemical-based propulsion, which is the amount of energy that's available for release is inherently set by how much energy is stored up in those chemical bonds, shown here in the case for oxygen combining with hydrogen. And as a direct result, the exhaust velocity, which can be achieved with these systems, is limited by how much energy is stored up per unit mass in that liquid and oxidizer fuel mixture that goes into the combustion chamber. As a direct result, the types of exhaust velocities that are achievable with chemical rockets can be limited. In contrast to that, electric propulsion kind of breaks free of the paradigm of chemical rockets, in which you have a limitation built into the choice of propellant. In electric propulsion systems, we rely on external power supplies to energize the propellant, as is shown qualitatively here with a power supply denoted as kind of a battery with a mass flow rate of typically a noble gas like xenon into the discharge chamber. The external power usually comes in the form of solar power, and in more advanced architectures being considered for 5 to 10 years down the road, potentially nuclear reactors. The major takeaway from this, however, is it can be shown just from a power balance that the exhaust velocities, or speed at which propellant comes out the back of that vehicle, generating the reactionary force, scales not with the energy per unit mass stored up in the propellant, but rather how much power is available supplied by the external power supply. And it's this versatility and flexibility is captured by this relationship that allows, in principle, electric propulsion systems to achieve much higher exhaust velocities that can be achieved by chemical rockets. As a direct extension of that, it's this enabling feature to achieve higher exhaust velocities that enables, in turn, higher fuel economy. So contrasting the two kind of expressions was shown here. On the left-hand side, chemical rockets are limited in terms of achievable exhaust velocity by the energy stored up per unit mass, and electric propulsion systems have more versatility in achieving exhaust velocities. So with that kind of takeaway in mind, we can contrast a chemical rocket system or architecture compared to an electric propulsion system, and finally kind of understand intuitively why EP systems can achieve higher fuel economy. So in moving in space and generating these reactionary force, you kind of have two asymptotic limits or extremes available to you in terms of how you generate that reactionary force. On the left-hand side, we have a chemical propulsion system, which expels mass out the back, generating force in the opposite direction. But in the case of the chemical propulsion system, because the exhaust velocity is relatively slow, as captured by that arrow in the lower left-hand corner moving in the opposite direction, the amount of mass that must be ejected can be quite large, generating that reactionary force. With electric propulsion systems, on the other hand, the exhaust velocity can be orders of magnitude higher. And as a direct result, for the same kind of inertia or momentum chance transfer that is desired, because momentum scales with mass times velocity, the required mass that must be expelled from the vehicle is much smaller. And as in turn, that leads to effectively larger fuel economy or improved fuel economy for these systems. They need to take less propellant on board, expel less propellant because it's sending at higher speed in order to achieve its orbital transfers. So the net takeaway from all of this is that because of the inherent physics of electric propulsion systems relying on an external power supply instead of stored up chemical energy, these systems can achieve much higher exhaust velocities and by extension, much higher fuel economy. So in practice, you can see kind of the disparity in two architectures for example, robotic mission on this slide. The propellant tanks to accomplish a given impulsive maneuver in space for a traditional chemical rocket might look something like this on the left-hand side. But if you leverage an electric propulsion system, the amount of propellant required on board is reduced by an order of magnitude. As a direct result, the overall mass of the vehicle that is launched into space is subsequently reduced. This again stretches back to the challenge that I outlined earlier for crewed exploration, which is, can you identify propulsion systems that have higher fuel economy that enable lower overall launch and lower overall mass of the vehicles that must be assembled in space. So with that in mind, electric propulsion, in large part because of these fuel economy or mass propellant savings in propellant mass, have been leveraged quite widely for robotic exploration and for applications closer to home. For station keeping, in the next 10 years, they project that over half of all satellites launched will have electric propulsion on board. Electric propulsion has already been used extensively by NASA for deep space exploration. I'm showing 2 robotic missions here, Dawn and Psyche. It's been leveraged for defense applications, providing rapid, maneuverable communication satellites. And then most recently, an application for electric propulsion is the constellations. SpaceX, most notably its Starlink constellation, uses electric propulsion on board to perform attitude control and drag makeup for providing Wi-Fi globally to the planet. So with that in mind, while EP is used extensively for robotic exploration applications, kind of the next leap forward is to see if it can be leveraged for crewed exploration. And as was alluded to earlier, electric propulsion already features quite heavily in the Artemis architecture returning to the moon, in which this gateway, which is a space station that will be based around the moon, has electric propulsion systems on board. But looking even further downstream for more ambitious architectures, there have been a number of proposals for how electric propulsion could be leveraged to support crewed exploration beyond the moon. And indeed, to kind of highlight again the advantages that stem from EP, you could go from a transfer vehicle, as shown here on the right-hand side, of this size to one which is substantially smaller, because the propellant tanks are reduced as you're leveraging a more fuel-efficient propulsion system on board. So with that in mind, and again, relating this back to the context of crewed exploration, there are a number of challenges that still need to be resolved for developing this type of EP-enabled architecture for crewed exploration. And I want to highlight 3 of those that we've been working on at the University of Michigan. The first is the challenge of power. And the second is a challenge of lifetime, and the third is the challenge of testing. So first, let me say a word about power. And to kind of highlight and illustrate this, I'm showing, turned on its side, one of the conventional types of electric propulsion that we develop in my laboratory and research in my laboratory, a so-called Hall effect thruster. I won't go into the details of the principle of operation of these systems, but suffice it to say, as with all other EP systems, it relies on the conversion of external power to generate energetic and accelerated thrust at very high speed. And you can see that propellant being accelerated downstream is captured by this luminous glow. So one thing that I've kind of failed to touch upon in discussing these concepts is that the amount of propulsive force generated by electric propulsion systems, in contrast to conventional rockets, is orders of magnitude lower. And indeed, to kind of highlight and illustrate that graphically, the amount of force that these systems generate is about equal to the weight of a couple of sheets of paper on your hand. If we were to dangle a sheet of paper over the thrust plume generated by this system, it would only have enough thrust to really support that sheet of paper or the action of gravity operating on that sheet of paper. If we were to put a heavier book on there, it'd immediately fall back down toward the thrust. So the net takeaway is that while electric propulsion systems have orders of magnitude improvement in fuel economy, conventional systems have relatively low thrust. And as a direct result of that, when you're looking at kind of deeper space architectures, the required transfer times are not these kind of Hohmann-based transfers in which you can directly go to your destination. They instead require continuous propulsive maneuvering in which the vehicle gradually spins up to get to its destination. These maneuvers in turn can take sometimes years or tens of years to get to their destinations. So the challenge from a perspective of crewed exploration is that, unlike robotic architectures where you can allow your vehicle to take years to get to its destination, for crewed exploration, we want to get there as fast as possible in order to increase the likelihood of the astronauts successfully making it to the destination. So one way we can kind of overcome this limitation is to explore concepts that operate at higher power. The central idea being that the thrust generated by an electric propulsion system scales directly with the amount of power that's available to that propulsion system. And to highlight that here, I'm showing a trade between the transit time required to get to Mars, assuming a 75 megaton payload, and a specific impulse that's typical for these systems, about 1,800 seconds, versus the amount of thruster power that's available for the system. And you can see that there's an inherent trade between the two. As you get to higher powers, the amount of force generated goes up, and as a direct result, the amount of transfer time goes down. And in turn, I've illustrated here and highlighted in blue kind of what we'd expect as reasonable transit times for crewed missions. So to kind of highlight the challenges that the field is currently facing, on this left red-hand line, you can see that the highest power Hall thrusters that have been flown to date have only operated about 5 kilowatts. And if we were to put just one of these systems on a 75 megaton payload, it would take 100 years for it to get to Mars. Of course, they do it quite fuel efficiently with an order of magnitude lower fuel required compared to the architectures using chemical rockets I highlighted earlier. But of course, ultimately the vehicle would get there and the crewed astronauts would not have made it. You can look at higher power systems that are currently underdeveloped to support that lunar gateway mission, and the transit times become more reasonable, but still are on the order of 11 to 10 years to get to its destination. So kind of the challenge in looking at crewed exploration enabled by electric propulsion is to identify concepts that have higher power available to them. Once you get to the 100 kilowatt or the megawatt level regime, crewed exploration actually becomes more feasible. And in fact, some cases can become faster than chemical-based propulsion systems. So to kind of, again, highlight this challenge that we're investigating in our research group is trying to identify propulsion concepts that can operate at these requisite power levels. So the next kind of follow-on question is what type of propulsion system is sufficient to answer the mail in terms of that requirement? And it turns out that there's a whole pantheon of different propulsion systems that are based off of electric propulsion that are available that could potentially satisfy this requirement. They fall under kind of 3 broad headings here that are differentiated based off the mechanisms that are leveraged to convert the external power into directed acceleration, including thermal expansion, electrostatic fields, electric fields, and electromagnetic acceleration. These tend to be more transient pulsed concepts. And that one of the key questions we're trying to go after in our lab and the broader community is which of these propulsion concepts is best suited for being extensible to higher power. And indeed, we've been focusing primarily on 3 concepts in our research group that we think are the most promising, including Hall effect thrusters, which I mentioned earlier, so-called pulse inductive thrusters, and then magnetoplasmodynamic thrusters. So let me say a quick word about some of the technological innovations that have come out of the lab in the past 5 years. The first one is this X3 engine. So on the left-hand side, I'm showing a conventional electric propulsion system that kind of represents the scale of propulsion systems and power levels that are used in space. And on the right-hand side, I'm illustrating a thruster concept that has been built and demonstrated that would potentially be used for a Mars-based architecture, in principle capable of operating up to 100 or 200 kilowatts. This is a concept that was designed by University of Michigan in conjunction with the Air Force Research Lab and the NASA Glenn Research Center. So this goes back to the initial slide I had in which I showed this thruster firing. You can see it on the left-hand side. To give you a sense of length scale, it's about 4 to 5 times larger in diameter compared to state-of-the-art propulsion systems that are flown. It's about 1 meter in diameter. So we took this system down to a NASA Glenn Research Center as part of a program that was sponsored by NASA, and we tested its propulsive generating capabilities as a function of discharge power. And that's what I'm going to show on the right-hand side. For context, I'm illustrating here as a yellow arrow the achievable thrust for kind of current thrusters on orbit, which is on the order of 300 to 500 millinewtons. Again, sufficient just to support a couple sheets of paper. And what we were able to demonstrate with this novel propulsion concept is that we could actually operate it at an order of magnitude higher power than conventional systems, achieving thrust levels on the order of 5 or 6 newtons, which in principle would be sufficient to support much more rapid crewed exploration missions. Indeed, it turned out to be one of the records set for this class of technology, and which was highlighted by space.com. And there's quite a bit of interest that was generated from this because it started to become feasible, started to become apparent that these technologies could in fact be leveraged if there are power available in space for supporting crewed exploration. And indeed, to that point, NASA supported over 3 years a number of different candidate technologies through the NASA Next Step program to establish if it's possible to develop architectures based off of these systems. And the X3 engine was one of those candidate engines. So kind of leaving the X3 aside, some other questions we've been going out for more recently is, can we achieve these power levels without having to increase commensurately the size of the vehicle? And the major driver from that is from a mission level perspective, in which it's recognized that as you increase the size of the thruster, you can get higher power and therefore more thrust. But at the same time, as you increase the size of the thruster, that introduces more mass penalty. So the amount of acceleration you're generating can in fact be canceled out by the increasingly large size of the thruster. So one strategy that we're investigating is, can we put kind of X3 level powers, 100 or 200 kilowatts, through a much smaller system, as shown here on the left-hand side? Can this smaller thruster generate the comparable levels of thrust as have been demonstrated for the X3? So this is a relatively recent research, and to highlight the key results here, again, I'm showing thrust as a function of discharge power. And you can see that the notional design point for the specific impulse we are operating here at 6 kilowatts. And we've been able to demonstrate that with minimal losses in efficiency and performance, we can in fact increase the amount of thrust generated by the system by a factor of 2. This is still a far cry from the order of magnitude increase that we'd like to achieve, but it has really served as a pathfinding exercise for how we might be able to achieve much higher powers through this more conventional technology, and by extension, achieve the types of architectures necessary for crewed exploration. I'll also make a quick plug here for some more novel and much lower TRL, technology readiness level technologies, that we are investigating. In particular, this is an RMF thruster, rotating magnetic field thruster, or a pulse inductive thruster. And the principal operation effectively is this is a plasma railgun that operates in space. And so we've been able to demonstrate that we can fire the system and achieve transiently 100 kilowatts per shot of operation. And we're exploring ways to improve performance and ultimately increase the average power that's generated by that. So again, this is to kind of illustrate that so far there are no clear winners yet for achieving the hundreds or megawatt levels of power necessary for rapid transfers, though there are some candidate technologies that have been identified. But one of the roles of the university, and Michigan in particular, is to try to establish at least the feasibility of these architectures that could ultimately be infused for enabling crewed exploration. In addition to that, I'll say as well, kind of looking to the future, we're actually going to take a turn and look to the past. One of the concepts that Professor Gallimore, who founded the lab in 1992, first investigated was magnetoplasmodynamic thrusters. And indeed, NASA has identified this as perhaps one of the most enabling technologies for supporting crewed exploration. So we hope to start looking at this technology in the near term as well. So in my remaining minute here, what I want to also highlight is leaving aside the challenge of power. Once we develop the concepts, there's also the question of how you test and validate these systems. And indeed, this turns out to be an equally, if not more important question, because you may end up developing a propulsion system, but you may not have the capability to actually validate it on the timescales required for crewed exploration. So to kind of highlight the challenge here in broad strokes, all of these propulsion systems that we're developing, because the thrust levels are so low, are only intended to operate in the environment of space. And as a direct result, we need to generate and use high fidelity vacuum space simulators. I'm showing here on the left-hand side one at the University of Michigan, which is one of the largest academic chambers in the world for this purpose. So effectively what we do is we evacuate the atmosphere in there, and then we fire the thruster in what we hope is a representative space-like environment. It turns out in practice, however, that there are many limitations for these test facilities, in so much as that they're not exactly representative of a space-like environment. This stems from the fact that there's residual pressure left over in the facility, so that the achievable background pressures are still orders of magnitude higher than you would anticipate in space. There are other challenges related to the fact that the facility itself has conducting walls, which represent boundary conditions, which would of course not be representative of space. And there are other sputtering material limitations as well. The key point underscoring all of this is that even the best facilities that are available to us in the world are not necessarily of creating a space-like environment. And it turns out that the problem for testing higher power concepts becomes even more pernicious. These so-called facility effects become more of a problem. So kind of recognizing this limitation, NASA recently released a solicitation for a university-led institute to try to go after this problem and to identify strategies that would enable testing higher power concepts as they become developed. Indeed, Michigan is one of the co-lead institutions, along with these other institutions, to go after this particular challenge in the next 5 years. This is a NASA Strategic Technology Research Institute, in which we will be effectively trying to address the question: if I have a 100 or 200 kilowatt level system, how can I make my facility most representative of space, or can I design strategies that enable that? So the center itself is going to be based at Georgia Tech under the direction of Professor Mitchell Walker. Michigan will be one of the co-lead institutions looking specifically at this problem of the role of facility-based pressure. So with that in mind, I'll close by returning again to this inaugural question, which is if we want to make a leap forward, a 1,000-fold leap forward from the moon to Mars, what kind of technologies do we need to facilitate that transfer? And some of the candidate technologies that we are looking at in Michigan include high power electric propulsion systems, as well as developing the infrastructure necessary to test those next generation concepts. And I'd like to highlight that I think Michigan is playing a leading role working with industry as well as government partners to address the key technical challenges that are related to this, developing this next generation architecture, and in turn, training the workforce that will support it once it becomes a reality. So I'll close here with this slide again, showing our facility and our workforce, 12 graduate students, all working toward developing next generation concepts to support this architecture, and hopefully continuing the legacy of Michigan supporting next generation technologies to enable access to the next frontier in space. So with that, I'll bring it to a close. Mark.
Thank you very much. Just like to close our celebration today with a number of thank yous, especially for our speakers and particularly for Dr. Warden, who actually came to visit us here in Ann Arbor. But also I'd like to thank all of our speakers, Dr. Hildberger, Dr. Jorns, and the Bliss team. It sounds very exciting, the projects they're doing. The organizations that help make this happen, the NASA Michigan Space Grant Consortium, and particularly like to thank Katie Klink and Deborah Warwick. Katie is our communications manager and event planner and project coordinator, and many hats, including helping with Zoom and Facebook Live. Also, I'd like to thank SPRL, the Space Physics Research Lab, Sue Lepre, and Pat McNally for their support. I'm going to turn it over to Mike Lamone at the end for the Michigan Space Institute. I'd also like to thank Tuija Pulkkinen, the chair of CLASP, as well as E.J. Olson, and also Tony Wass, the chair of Aerospace Engineering, as well as all of the team that he has here, Chris Chartier and Gwen Brown and Kimberly Johnson, supported us physically here in the FXB. And the last but not least, the College of Engineering and Alec Gallimore for his support. So tonight, or actually tomorrow night at 9:50, if you're in Ann Arbor and a clear night, the International Space Station actually flies directly overhead. I think it will reach about 87 degrees, essentially straight up at 9:50. And also the Perseid meteor showers watch over the next week. And for those in Ann Arbor, we're celebrating the splashdown of Apollo 15, which happens in 1 week. The crew spent about 3 days on the surface of the moon, and it took a little bit more than 3 days to get back home. And we'll be celebrating with summer ice cream. So with that, I'd like to turn it over to Professor Mike Lamone of the Michigan Space Institute to close us out.
All right, well, thank you all for participating today, and it looks like we've had a great crew of attendees throughout the day. Again, I would also like to say thank you to all of our speakers throughout the day, and also to the staff, especially Katie Klink and Deborah Warwick, who helped organize today's event. I'd also like to extend a special thanks to Mark Baldwin for for all of the work that he has done. He's been the leader of this entire effort from the very beginning, and so really like to say thank you, and a round of applause for him and his efforts on making this day a reality for us. So, so with that, thank you all very much. And thank you for attending. I think this was a great celebration of Michigan in space.
Thank you, everyone. Have a good weekend.